Tonight on The Sleepy Scientist, we're drifting gently across the cosmic void to our nearest celestial neighbor, exploring the profound mysteries NASA has uncovered on the Moon's hidden far side. From the ancient secrets locked in lunar craters to the surprising discoveries made by robotic explorers, we'll journey through the peaceful science of lunar exploration and discover what the Moon's darkest face reveals about our solar system's violent past. In the quiet darkness above our heads, where Earth's gravitational embrace holds our faithful companion in its ancient dance, there exists a world within a world, a hemisphere of our Moon that has remained hidden from human eyes for all of recorded history. Until the dawn of the space age, this far side of the Moon, sometimes mistakenly called the dark side, harbors secrets that have reshaped our understanding of planetary formation, cosmic bombardment, and the violent early history of our solar system. For millennia, humans have gazed upward at the Moon's familiar face, seeing the same patterns of light and shadow that our ancestors observed, never knowing that our celestial companion possessed an entirely different hemisphere, a mysterious realm of ancient craters, towering mountain ranges, and geological features unlike anything visible from Earth. The Moon's far side remained one of the solar system's greatest mysteries, until robotic explorers first revealed its secrets in 1959. Tonight, as we embark on this peaceful journey across the lunar landscape, we'll discover how NASA's decades of exploration have unveiled the far side's remarkable geology, its role as a cosmic time capsule preserving evidence of the solar system's tumultuous youth, and its potential as humanity's next frontier for scientific discovery and exploration. We'll learn how this hidden hemisphere differs dramatically from the familiar near side we see each night, and why these differences hold crucial clues to understanding not just lunar history, but the formation and evolution of the entire Earth-Moon system. The story we'll tell unfolds across billions of years and spans from the Moon's violent birth in a cosmic collision to the sophisticated robotic missions that now map its surface in exquisite detail. We'll explore how the far side's heavily cratered terrain serves as a museum of cosmic impacts, preserving a record of the intense bombardment that shaped all the inner planets during the solar system's chaotic infancy. As we prepare to journey to this hidden world, we carry with us the accumulated wisdom of 6 decades of lunar exploration, from the first grainy images transmitted by Lunar 3 to the high-resolution maps created by modern orbiters, from the samples collected by Apollo astronauts to the detailed chemical analyses performed by robotic landers. Each mission has added new pieces to the puzzle of lunar science and revealed new mysteries waiting to be solved. We'll discover how the Moon's far side serves as humanity's window into the deep past, preserving impact craters and geological features that have long since been erased from Earth's dynamic surface by plate tectonics, erosion, and volcanic activity. The ancient scars visible on the lunar far side tell the story of the late heavy bombardment, a period of intense cosmic violence that may have delivered the water and organic compounds necessary for life to emerge on Earth. Our exploration will also carry us forward in time to consider the Moon's role in humanity's future, as space agencies around the world plan permanent lunar bases and use the far side's unique properties for revolutionary astronomical observations. The radio-quiet environment of the lunar far side, naturally shielded from Earth's radio interference, may soon host telescopes capable of observing the universe's earliest epochs and searching for signals from distant civilizations. As we begin this gentle drift across the cosmic gulf that separates our world from its companion, let us approach the Moon with the reverence it deserves, not as a distant, lifeless rock, but as an active participant in Earth's history, a cosmic laboratory that has preserved evidence of processes that shaped our entire planetary neighborhood, and a stepping stone toward humanity's expansion into the solar system. As we drift deeper into understanding our lunar companion, we must first appreciate the profound asymmetry that defines the Moon's character, the dramatic differences between the hemisphere we see from Earth and the mysterious far side that remained hidden until the space age. This dichotomy, more striking than the differences between any two hemispheres of Earth, tells a fundamental story about lunar evolution and the forces that have shaped our celestial neighbor over billions of years. The near side of the Moon, familiar to every human who has ever gazed upward at night, presents a landscape of dark maria ancient lava plains that early observers mistook for seas interspersed with bright highland regions peppered with craters of various sizes. These dark areas, created by massive volcanic eruptions billions of years ago, give the Moon its distinctive appearance and create the patterns that cultures worldwide have interpreted as faces, animals, or mythological figures. The maria cover approximately 31% of the near side's surface, creating vast smooth plains that formed when massive asteroid impacts fractured the lunar crust and allowed subsurface magma to flow onto the surface. Mare Tranquillitatis, where Apollo 11 first landed, Mare Imbrium, Mare Serenitatis, and the other familiar dark regions represent some of the largest volcanic features in the solar system, each one a testament to the Moon's once active geological past. In stark contrast, the far side presents an almost entirely different world, a hemisphere dominated by heavily cratered highlands with virtually no maria. Only about 2% of the far side's surface consists of these dark volcanic plains, creating a landscape that appears uniformly bright and heavily scarred by billions of years of impact bombardment. This dramatic asymmetry immediately raises profound questions about lunar evolution and the forces that created such different hemispheres on a single world. The highland regions that dominate the far side consist primarily of an all-vital light-colored rock, rich in the mineral plagioclase feldspar that formed when the Moon's original magma ocean slowly cooled and crystallized over tens of millions of years. These ancient highlands represent some of the oldest rocks in the solar system, preserving a record of processes that occurred during the Moon's formation, approximately 4.5 billion years ago. The crater density differences between the two hemispheres provide crucial evidence about the Moon's geological history. The far side's heavily cratered terrain preserves impact scars dating back billions of years, while many near-side regions show evidence of more recent geological activity that has erased or buried ancient craters. This preservation difference makes the far side an invaluable window into the solar system's violent past. Elevation differences add another dimension to the Moon's asymmetric character. The far side generally sits at higher elevations than the near side, with some regions rising more than 10 kilometers above the mean lunar radius. The South Pole Aitken Basin, the largest impact structure on the Moon's far side, creates one of the most dramatic topographic features in the solar system, a depression so vast and deep that it exposes materials from deep within the lunar interior. The magnetic field differences between the two hemispheres provide additional evidence of the Moon's asymmetric evolution. While the Moon lacks a global magnetic field today, localized magnetic anomalies scattered across the surface suggest it once possessed a dynamo-generated field similar to Earth's. These magnetic signatures are distributed unevenly between the hemispheres, with some of the strongest anomalies located on the far side, hinting at different geological histories. Chemical composition variations between the near and far sides reflect their different evolutionary paths. Samples returned by Apollo missions and analyzed by orbital instruments reveal that the near side contains higher concentrations of heat-producing radioactive elements like uranium, thorium, and potassium. This radioactive heating may have contributed to the extensive volcanism that created the near side's maria while the far side remained relatively inactive. The thickness of the lunar crust varies dramatically between the two hemispheres, with the near side crust averaging about 60 kilometers thick while the far side crust extends to depths of 100 kilometers or more in some regions. This crustal thickness asymmetry may explain why volcanism was more common on the near side. Thinner crust provided easy pathways for magma to reach the surface, while the thicker far side crust acted as a barrier to volcanic activity. Gravitational field measurements reveal additional evidence of the Moon's internal asymmetry. The near side shows numerous positive gravitational anomalies, called Marskin's concentrations of dense material beneath the maria, that may represent solidified magma chambers or metallic impactor material. The far side displays fewer and weaker Marskins, consistent with its history of reduced volcanic activity and different impact characteristics. Temperature variations between the hemispheres reflect their different surface properties. and compositions. The dark maria of the near side absorb more solar energy and reach higher daytime temperatures than the bright highland regions that dominate the far side. These temperature differences drive different patterns of thermal cycling and may influence processes like space weathering and volatile transport across the lunar surface. The distribution of volatile compounds like water ice appears to differ between the hemispheres, though our understanding of these differences continues to evolve with new observations. Permanently shadowed regions near both lunar poles contain deposits of water ice, but the accessibility and abundance of these resources may vary between near-side and far-side locations, affecting future exploration strategies. Seismic activity recorded by Apollo-era instruments revealed that the Moon experiences different types of internal dynamics between its hemispheres. Deep moonquakes, likely caused by tidal stresses from Earth's gravitational pull, show patterns that may be influenced by the Moon's internal asymmetries and the different crustal structures of the near and far sides. The space weathering processes that gradually alter lunar surface materials operate differently across the two hemispheres due to their distinct compositions and exposure histories. The iron-rich basalts of the near-side maria develop different optical properties over time compared to the aluminum-rich unorthosites of the far-side highlands, creating measurable spectral differences observable from Earth and spacecraft. Understanding the Moon's two-faced nature has required decades of patient observation and analysis, combining telescopic studies from Earth with detailed investigations by lunar orbiters, landers, and sample return missions. Each new dataset reveals additional complexity in the Moon's asymmetric character and raises new questions about the processes that created and maintained these dramatic hemispheric differences over billions of years. The implications of lunar asymmetry extend beyond academic curiosity to practical considerations for future exploration. The different characteristics of the near and far sides create distinct opportunities and challenges for scientific investigation, resource utilization, and the establishment of permanent human presence. Understanding these differences is crucial for planning missions that can take advantage of each hemisphere's unique properties. As we continue our journey toward the Moon's hidden face, we carry with us an appreciation for the profound asymmetries that make our celestial companion one of the most geologically complex small worlds in the solar system. The dramatic differences between the familiar near side and mysterious far side serve as constant reminders that even our closest cosmic neighbor harbors surprises and continues to challenge our understanding of planetary formation and evolution. Let us float gently toward understanding one of the most fundamental aspects of the Earth-Moon system, the celestial mechanics that ensure we always see the same face of our lunar companion, while its far side remains perpetually hidden from our view. This phenomenon, known as synchronous rotation or tidal locking, represents one of the most elegant demonstrations of gravitational physics in action, and plays a crucial role in maintaining the stability that has allowed life to flourish on Earth. The Moon's synchronous rotation means that it completes one rotation on its axis in exactly the same time it takes to complete one orbit around Earth, approximately 27.3 days. This precise coordination ensures that the same hemisphere always faces Earth, while the opposite hemisphere remains forever turned away. This arrangement is not a cosmic coincidence, but rather the inevitable result of gravitational forces acting over billions of years to gradually slow the Moon's rotation until it became locked to its orbital period. The process that created this tidal locking began shortly after the Moon's formation, when our satellite was much closer to Earth, and both bodies were spinning much faster than they do today. In those early epochs, the Moon likely rotated once every few hours, presenting different faces to Earth as it spun. However, Earth's powerful gravitational field began working to synchronize the Moon's rotation with its orbital motion through a process involving tidal bulges and energy dissipation. Earth's gravity doesn't pull uniformly on the Moon. Due to the inverse square law, parts of the Moon closer to Earth experience slightly stronger gravitational pull than parts farther away. This differential force creates tidal bulges in the Moon's shape, stretching it slightly along the Earth-Moon line. As the Moon rotated faster than its orbital period, These tidal bulges tried to rotate with the Moon's surface, but Earth's gravity worked to keep them aligned with Earth. The friction created by this constant flexing and relaxation of the Moon's shape gradually drained rotational energy from the Moon's spin while transferring some of that energy to the Moon's orbital motion. This process, operating over hundreds of millions of years, slowly reduced the Moon's rotation rate while simultaneously increasing its distance from Earth. Eventually, the Moon's rotation slowed to match its orbital period, creating the stable configuration we observe today. The same tidal forces that lock the Moon's rotation also affect Earth, though the process operates more slowly due to our planet's much larger mass. The Moon's gravitational pull creates tidal bulges in Earth's oceans and, to a lesser extent, in the solid Earth itself. As our planet rotates faster than the Moon orbits, these tidal bulges try to stay aligned with the Moon, creating friction that gradually slows Earth's rotation while pushing the Moon into a higher, more distant orbit. This ongoing tidal interaction means that Earth's days are gradually lengthening, while the Moon slowly spirals away from Earth. Currently, each day grows longer by about 1.7 milliseconds per century, while the Moon recedes at approximately 3.8 centimeters per year, a rate precisely measured using laser reflectors placed on the lunar surface by Apollo astronauts. This process will continue until Earth and Moon become mutually tidally locked, with both showing the same face to each other permanently. The Moon's synchronous rotation creates the phenomenon known as libration subtle rocking motions that allow Earth-based observers to see slightly more than half of the Moon's surface over time. These librations result from the Moon's slightly elliptical orbit and the small tilt of its rotational axis relative to its orbital plane. Through careful observation over many months, astronomers can see about 59% of the Moon's surface from Earth, but the remaining 41% remained completely hidden until spacecraft could travel beyond our planet. Physical libration occurs because the Moon's orbit is elliptical rather than perfectly circular, causing its orbital velocity to vary according to Kepler's laws of planetary motion. When the Moon moves faster in the portion of its orbit closest to Earth, its rotation can't keep pace with the changing orbital position, causing it to rock back and forth slightly. This allows observers on Earth to see a bit farther around the Moon's eastern and western limbs at different times. Latitudinal libration results from the 6.7-degree tilt between the Moon's equator and its orbital plane around Earth. This tilt causes the Moon to nod up and down relative to Earth's perspective, allowing observers to see slightly over the Moon's north and south poles at different times. During its orbit, these combined librations create complex patterns of visibility that skilled observers can track using telescopes and detailed lunar maps. The synchronous rotation that keeps the Moon's facade hidden has profound implications for both worlds. For the Moon, it means that one hemisphere experiences the extreme temperature variations of lunar day and night every 27.3 Earth days, while both hemispheres receive equal amounts of solar illumination over time, dispelling the common misconception that the far side is permanently dark. The dark side terminology refers to its hiddenness from Earth, not to any permanent absence of sunlight. For Earth, tidal locking has created a stabilizing influence on our planet's rotational axis. The Moon's gravitational pull helps maintain Earth's axial tilt at approximately 23.5 degrees, preventing the chaotic changes in orientation that might otherwise occur due to gravitational perturbations from other planets. This stability has been crucial for maintaining relatively stable climate patterns that allowed life to evolve and develop complex ecosystems over billions of years. The mechanics of tidal locking operate throughout the solar system, creating many examples of synchronously rotating bodies. Most large moons of the gas giant planets are tidally locked to their parent planets, including Jupiter's four largest moons, Saturn's major satellites, and many smaller moons throughout the outer solar system. This widespread occurrence demonstrates that tidal locking represents a natural and inevitable outcome of gravitational dynamics in close orbital relationships. The precise nature of the Moon's tidal locking has enabled remarkably accurate predictions and measurements of lunar motion. Ancient eclipse records from Babylon, China, and other civilizations allow astronomers to trace the Moon's orbital evolution backward through history and detect subtle changes in Earth's rotation rate over millennia. These historical records provide crucial data for understanding long-term changes in the Earth-Moon system. Modern laser ranging experiments using retroflectors placed on the Moon by Apollo missions and Soviet lunar probes can measure the Moon's distance to within a few centimeters, revealing subtle variations in lunar orbit caused by tidal interactions, gravitational perturbations from the Sun and planets, and even relativistic effects predicted by Einstein's general theory of relativity. These measurements represent some of the most precise determinations of celestial mechanics ever achieved. The engineering implications of the Moon's synchronous rotation have influenced spacecraft design and mission planning since the beginning of lunar exploration. Missions to the Moon's side face unique communication challenges, since direct radio contact with Earth is impossible from the hidden hemisphere. This limitation requires relay satellites positioned in special orbits around the Moon, or at gravitationally stable Lagrange points to maintain communication links. Future lunar exploration will continue to grapple with the consequences of synchronous rotation, as permanent bases on the far side will require sophisticated communication infrastructure to maintain contact with Earth. However, this same isolation that creates communication challenges also provides unique opportunities for radio astronomy, as the Moon's bulk shields the far side from Earth's radio interference, creating the quietest radio environment in the inner solar system. The beauty of synchronous rotation lies not just in its mechanical precision, but in its role as a cosmic timekeeper that has maintained stability for billions of years. This gravitational dance between Earth and Moon continues to evolve slowly, carrying both worlds toward a distant future when they will face each other permanently, across the vastness of space, locked in eternal gravitational embrace while the Sun gradually ages and transforms around them. As we prepare to journey to the Moon's hidden hemisphere, we carry with us an appreciation for the elegant gravitational choreography that has kept this realm concealed from human eyes for all of history until the dawn of space exploration. Understanding why we never see the far side helps us appreciate both the precision of celestial mechanics and the remarkable achievement represented by our ability to finally explore this hidden world through robotic emissaries and human ingenuity. Our peaceful journey now takes us to one of the most momentous occasions in the history of space exploration, October 7, 1959, when humanity first glimpsed the Moon's mysterious far side through the mechanical eyes of Lunar 3, a small Soviet spacecraft that forever changed our understanding of our celestial companion. This historic mission represents not just a technological achievement, but a profound expansion of human consciousness, revealing an entirely unknown hemisphere of the world that had accompanied Earth through billions of years of cosmic evolution. Lunar 3 launched on October 4, 1959, exactly 2 years after Sputnik 1 opened the space age. This modest spacecraft, weighing just 278 kilograms, carried a relatively simple camera system that would accomplish something no human eyes had ever achieved: photographing the hidden hemisphere that had remained concealed since the Moon became tidally locked to Earth billions of years earlier. The mission represented both the culmination of early space technology and the beginning of planetary exploration as we know it today. The spacecraft's trajectory required precise calculations to position it beyond the Moon, where it could photograph the far side while maintaining communication with Earth. Soviet engineers designed a complex flight path that would carry Lunar 3 around the Moon's eastern limb, allowing it to photograph the hidden hemisphere during a brief window when both the far side would be illuminated by the Sun and the spacecraft could transmit its images back to Earth before disappearing behind the Moon's bulk. The camera system aboard Lunar 3 represented cutting-edge technology for its era, a dual-lens photographic system that could capture images on 35mm film and then process and scan them for radio transmission back to Earth. This ambitious approach required the spacecraft to carry a complete photographic laboratory, including film processing chemicals and a scanning system that could convert photographic images into radio signals suitable for transmission across the vast gulf of space. On October 7, 1959, as Lunar 3 swung around the Moon's far side, its cameras began their historic work. Over the course of 40 minutes, the spacecraft captured 29 photographs covering approximately 70% of the far side's surface. These images, though crude by modern standards, revealed for the first time the dramatically different character of the Moon's hidden hemisphere, a landscape dominated by ancient craters and bright highland terrain. Unlike the familiar Maria-covered near side visible from Earth, the technical challenges of transmitting these images across the 180,000 kilometers of space pushed 1950s technology to its limits. The spacecraft's radio system could only transmit at extremely low data rates, requiring hours to send each photograph line by line back to waiting receivers on Earth. Atmospheric conditions and the spacecraft's tumbling motion further complicated the transmission process, making successful image recovery a remarkable achievement of early space communications. The first images received on Earth were of poor quality, showing only the gross features of the far side's topography. However, even these grainy photographs immediately revealed that the hidden hemisphere looked nothing like the near side familiar to Earth-based observers. Instead of the dark Maria that characterized the visible face, the far side appeared uniformly bright, heavily cratered, and ancient, a landscape that had apparently remained unchanged for billions of years. Soviet scientists worked carefully to enhance and interpret the Lunar 3 images, creating the first maps of the lunar far side and beginning the process of nomenclature that would name features on the hidden hemisphere. They designated Mare Moscovitz, Sea of Moscow, as the first far side mare, along with craters honoring Russian scientists like Tsiolkovsky and Lomonosov. This naming process established precedents for lunar nomenclature that continue today through the International Astronomical Union. The scientific impact of Lunar 3's discovery extended far beyond simple photography. The images provided the first evidence that the Moon possessed global asymmetry, that the two hemispheres had evolved along different paths, despite forming as parts of the same world. This asymmetry would become one of the central puzzles of lunar science, driving decades of research into the processes that could create such dramatically different hemispheres on a single body. The absence of large Maria on the far side immediately raised questions about lunar volcanism and crustal evolution. Why had the massive basaltic eruptions that created the near side S Maria failed to occur on the far side? The Lunar 3 images provided the first hints that the Moon's geological history was far more complex than previously imagined, with different hemispheres experiencing different evolutionary pathways over cosmic time. The heavily cratered appearance of the far side suggested that this hemisphere had preserved a more complete record of impact bombardment than the near side, where many ancient craters had been buried or erased by volcanic activity. This preservation made the far side a potential cosmic museum, holding evidence of the intense bombardment that had affected all inner solar system bodies during their early history. Lunar 3's success inspired continued Soviet lunar exploration and spurred American efforts to develop their own lunar reconnaissance capabilities. The mission demonstrated that robotic spacecraft could serve as effective surrogates for human exploration, opening possibilities for detailed study of worlds far beyond Earth's reach. The techniques developed for Lunar 3's imaging and communication systems would influence spacecraft design for decades to come. The psychological impact of seeing the Moon's far side for the first time resonated beyond the scientific community. These images represented humanity's first glimpse of a completely alien landscape, a world that existed within our cosmic neighborhood but had remained forever hidden from human perception. The revelation that our familiar Moon possessed an entirely unknown hemisphere expanded human consciousness and demonstrated the power of space exploration to reveal new realms of knowledge. Follow-up analysis of the Lunar 3 images continued for years after the mission's completion, as scientists worked to extract maximum information from the precious photographs. Careful photogrammetric analysis revealed elevation differences, crater size distributions, and albedo variations that provided clues about the far side's composition and geological history. These early studies established the foundation for all subsequent far side research. The mission also demonstrated the international dimensions of lunar exploration, as Soviet scientists shared their far-side images with colleagues around the world despite the ongoing Cold War tensions. This scientific cooperation established precedents for international collaboration in lunar research that would eventually lead to shared databases, coordinated missions, and global scientific partnerships in exploring the Moon. Technical lessons learned from Lunar 3 influenced the design of subsequent lunar missions, particularly in the areas of spacecraft stabilization, photographic systems, and long-distance communication. The mission's successes and limitations provided valuable experience that would be incorporated into more sophisticated orbiters and landers designed to conduct detailed studies of both lunar hemispheres. The Lunar 3 images also provided the first observational data for testing theories about lunar origin and evolution. The stark differences between the near and far sides offered new constraints for models of lunar formation, whether through capture, co-accretion with Earth, or giant impact scenarios. These observations would prove crucial as scientists developed increasingly sophisticated models of early solar system dynamics. Lunar 3's legacy extends beyond its immediate scientific contributions to its role as a pioneering step in planetary exploration. The mission established the principle that robotic spacecraft could serve as humanity's ambassadors to other worlds, gathering data and images that would be impossible to obtain from Earth-based observations alone. This approach would become the foundation for all subsequent planetary exploration missions. As we continue our journey toward understanding the Moon's hidden face, we carry with us gratitude for the courage and ingenuity of the engineers and scientists who made Lunar 3 possible. Their achievement in revealing the Fascinates secrets represents a milestone in human knowledge, comparable to the first maps of unknown continents or the first glimpses through early telescopes. The grainy images transmitted by this modest spacecraft opened a new chapter in lunar science and planetary exploration that continues today. As we drift deeper into the story of lunar exploration, we encounter the magnificent achievement of the Apollo program, humanity's first direct investigation of another world and our most comprehensive exploration of the Moon to date. While the Apollo missions focused primarily on near-side landing sites visible from Earth, they provided crucial insights into lunar composition, structure, and history that transformed our understanding of the far side and established the scientific foundation for all subsequent lunar research. The Apollo program represented an unprecedented expansion of human presence beyond Earth, with 12 astronauts walking on the lunar surface during 6 successful landing missions between 1969 and 1972. These brave explorers became humanity's first planetary field geologists, collecting samples, conducting experiments, and making observations that would revolutionize lunar science and provide the empirical data needed to understand both hemispheres of our celestial companion. Apollo 11's historic first landing in the Sea of Tranquility on July 20, 1969, marked humanity's initial direct contact with another world. Neil Armstrong and Buzz Aldrin spent just over 21 hours on the lunar surface, collecting 21.5 kilograms of samples that provided the first detailed chemical and mineralogical analysis of lunar material. These samples revealed that the Moon's surface consisted primarily of basaltic rocks, formed by ancient volcanic eruptions, establishing the volcanic origin of the dark maria visible from Earth. The sample return capabilities of Apollo missions provided unprecedented insights into lunar chronology through radiometric age dating. Rocks collected from various landing sites revealed that the major mare volcanism occurred primarily between 3.2 and 3.8 billion years ago, with some extending as recently as 3.0 billion years ago. This timing helped establish the sequence of events in lunar history and provided calibration points for crater counting techniques used to estimate the ages of surfaces throughout the solar system. Apollo 12's precision landing near the Surveyor 3 spacecraft demonstrated improved navigation capabilities while collecting samples from Oceanus Procellarum, revealing the diversity of mare compositions across different regions. The mission's samples showed that lunar basalts varied significantly in their titanium content, iron abundance, and trace element signatures, indicating that different mare regions had been supplied by distinct magma sources from deep within the Moon's interior. The Apollo 14 mission to Fremora crater provided the first samples of highland material excavated from the Moon's ancient crust. These samples, composed primarily of unorthositic breccias, supported theories that the Moon had once been covered by a global magma ocean that differentiated to form a plagioclase-rich crust floating on a denser interior. This discovery provided crucial insights into the Moon's earliest history and the processes that formed the highland terrain dominating the far side. Apollo 15 introduced the first lunar rover and extended exploration capabilities, allowing astronauts to travel greater distances and collect samples from more diverse geological settings. The mission's exploration of Hadley Apennine revealed the structure of lunar mountain ranges formed by large impact events, while samples from the nearby Rill system provided insights into ancient volcanic processes that had created some of the Moon's most dramatic topographical features. The scientific instruments deployed by Apollo missions revolutionized our understanding of lunar internal structure and ongoing geological processes. Seismometers placed on the surface detected moonquakes caused by tidal stresses from Earth's gravitational pull, meteorite impacts, and occasional deep seismic events that revealed the Moon's internal layered structure. These seismic networks operated for years after the astronauts' departure, providing long-term monitoring of lunar activity. Apollo 16's exploration of the Descartes Highlands provided the first detailed samples from what scientists believed to be ancient volcanic terrain but proved to be impact breccias rocks, formed by the shattering and melting that occurs during large asteroid collisions. This discovery revolutionized understanding of highland formation and demonstrated that impact processes had played a much larger role in shaping lunar terrain than previously recognized. The final Apollo mission, Apollo 17, combined the geological expertise of scientist astronaut Harrison Schmitt with enhanced exploration capabilities to conduct the most comprehensive surface investigation of the program. The mission's samples from the Taurus-Littrow Valley revealed evidence of ancient volcanism different from the typical mare basalts, including orange glass beads formed by explosive volcanic eruptions that had distributed material across vast distances. Heat flow experiments conducted during Apollo missions revealed that the Moon generates much less internal heat than Earth, confirming that our satellite had cooled significantly since its formation. These measurements provided crucial constraints on lunar thermal evolution and helped explain why volcanic activity had ceased on the Moon while continuing on the larger, more thermally active Earth. The laser retroflector rays placed on the lunar surface by Apollo 11, 14, and 15 continue to serve science today, allowing precise measurements of the Moon's distance and orbital evolution. Through laser ranging experiments, these measurements have revealed that the Moon is gradually spiraling away from Earth due to tidal interactions, while also providing tests of Einstein's general theory of relativity and precise measurements of lunar librations and orbital dynamics. Magnetic field measurements by Apollo surface experiments and orbital instruments revealed that the Moon currently lacks a global magnetic field, but contains localized magnetic anomalies that suggest it once possessed an active magnetic dynamo. These paleomagnetic signatures, preserved in lunar rocks and surface features, provided evidence that the early Moon had a more active interior with convective processes capable of generating magnetic fields. The Apollo mission's orbital photography and mapping provided the first high-resolution images of both lunar hemispheres, revealing the detailed topography and geological relationships that ground-based telescopes could not resolve. These orbital surveys created the foundation for all subsequent lunar mapping and established the photographic database that would guide future robotic missions to both sides of the Moon. Analysis of Apollo samples revealed the presence of solar wind particles implanted in lunar surface materials, providing direct evidence of the stream of charged particles flowing from the Sun throughout the solar system's history. These solar wind signatures offered insights into the ancient Sun's behavior and demonstrated how airless bodies like the Moon serve as collectors of solar radiation and cosmic materials. The Apollo program also established important precedents for planetary protection and sample curation that continue to influence space exploration today. The quarantine procedures used for returning astronauts and samples, while ultimately unnecessary due to the Moon's sterile nature, demonstrated humanity's responsibility to prevent biological contamination between worlds as we expand our presence throughout the solar system. Perhaps most importantly for understanding the far side, Apollo missions provided the ground truth needed to calibrate remote sensing techniques and orbital observations. The detailed chemical and mineralogical analyses of Apollo samples created reference standards that allowed scientists to interpret spacecraft data from unexplored regions, including the far side territories that remained inaccessible to direct sampling. The scientific legacy of Apollo extends far beyond the immediate results of the missions themselves. The samples, data, and analytical techniques developed during the program continue to yield new insights, as improved laboratory methods and theoretical understanding allow scientists to extract information that was impossible to obtain using 1970s technology. These samples represent a permanent scientific resource that will continue serving lunar research for generations to come. The technological achievements of Apollo also established the engineering foundation for all subsequent lunar missions, demonstrating spacecraft design principles, navigation techniques, and life support systems that would influence decades of robotic exploration. The program's success proved that humans could survive and work effectively in the lunar environment, paving the way for future long-duration missions and permanent lunar installations. As we continue our exploration of the Moon's hidden mysteries, we carry with us the profound legacy of Apollo, not just as a demonstration of human courage and technological capability, but as the foundation of our scientific understanding of lunar processes and evolution. The knowledge gained through these missions provides the context needed to appreciate the significance of discoveries on the far side and understand how both hemispheres fit into the larger story of lunar and planetary evolution. Let us float gently toward the most striking geological mystery. Our Moon presents the dramatic differences between the far side's ancient, heavily cratered highlands and the near-side smoother Maria-covered plains. This hemispheric asymmetry represents one of the most profound puzzles in planetary science, revealing that our celestial companion underwent radically different geological evolution on its two faces. Despite forming as a single body in the same cosmic environment, the far side's landscape presents a vast museum of impact cratering that preserves the violent history of the inner solar system's early epochs. Unlike the near side, where extensive volcanism filled many large impact basins with dark basaltic lavas, the far side retains the scars of virtually every major collision that has occurred since the Moon's formation. This preservation makes the hidden hemisphere an invaluable record of the late heavy bombardment and earlier impact events that shaped all terrestrial planets. The most dominant geological features of the far side are the ancient highland terrains, composed primarily of unorthositic rocks-like colored materials rich in the mineral plagioclase, feldspar that formed when the Moon's primordial magma ocean slowly cooled and differentiated. These highlands represent some of the oldest crustal materials in the solar system, dating to over 4.4 billion years ago when the Moon was still hot from its formation and covered by an ocean of molten rock hundreds of kilometers deep. The South Pole Aitken Basin dominates the far side's southern hemisphere as the largest and oldest recognizable impact structure on the Moon. This enormous basin, stretching over 2,500 kilometers from rim to rim and excavating materials from depths of up to 13 kilometers below the original surface, provides a window into the Moon's deep interior structure and early crustal evolution. The impact that created this basin was so massive that it may have excavated material from the lunar mantle, offering unique insights into the Moon's internal composition. Crater morphology on the far side reveals the effects of billions of years of continuous bombardment and erosion. The oldest craters show heavily degraded rims and floors filled with debris from subsequent impacts, creating a complex layered stratigraphy that records the chronological sequence of impact events. Younger craters preserve sharp rims and well-defined ejecta blankets, allowing scientists to study the mechanics of impact processes and crater formation under lunar conditions. The absence of extensive mare volcanism on the far side creates one of lunar science's greatest puzzles. While the near side experienced massive basaltic eruptions that filled impact basins and created the familiar dark plains visible from Earth, similar eruptions were rare on the far side. Only about 2% of the far side's surface consists of mare materials, concentrated primarily in mare moscovines and a few smaller patches within large impact basins. This volcanic asymmetry appears to be related to differences in crustal thickness between the hemispheres. The far side's crust averages 100 kilometers or more in thickness compared to the near side's 60-kilometer average, creating a barrier that prevented most magmas from reaching the surface. The thicker crust required more energy to fracture and provided longer pathways for ascending magma to cool and solidify before erupting, effectively suppressing the volcanism that was so prominent on the thinner crusted near side. The distribution of radioactive elements provides additional insights into the far side's geological evolution. Heat-producing isotopes of uranium, thorium, and potassium are much less abundant on the far side than on the near side, creating lower internal temperatures and reducing the likelihood of partial melting that could generate volcanic eruptions. This compositional asymmetry may have been established during the Moon's earliest differentiation processes or could result from large impact events that redistributed materials between the hemispheres. Impact melt deposits scattered across the far side preserve evidence of the intense energy released during large collisions. These glassy materials, formed when rock was melted and rapidly cooled during impact events, provide samples of target materials that existed at various depths within the lunar crust. Analysis of impact melts allows scientists to reconstruct the composition and structure of the Moon's interior without requiring direct drilling or excavation. The far side's crater chains and secondary crater fields record the complex trajectories of debris ejected during major impact events. When large asteroids or comets strike the Moon, they excavate enormous amounts of material that travels in ballistic trajectories before impacting elsewhere on the surface. The preservation of these secondary crater patterns on the far side provides insights into the physics of impact processes and the distribution of ejector materials across planetary surfaces. Central peak complexes within far side craters reveal the deep crustal structure through the materials they expose. During large impact events, the tremendous pressures and temperatures created by the collision cause crustal rocks to rebound upward, forming central peaks that bring deep materials to the surface where they can be studied by orbital instruments. These natural drilling operations provide access to rocks that formed kilometers below the original surface. Peak ring basins on the far side represent some of the most complex impact structures in the solar system. These multi-ring formations, created by the largest impact events, show how planetary crusts respond to extreme shock and deformation. The preserved morphology of far side peak ring basins provides insights into impact mechanics that have been obscured by later geological processes on more active worlds like Earth. The far side's lack of atmospheric or hydrological weathering has preserved surface textures and compositions that would be quickly altered on Earth. Space weathering processes caused by micrometeorite impacts, solar wind bombardment, and cosmic ray exposure operate slowly on the Moon, allowing ancient geological relationships to remain visible for billions of years. This preservation makes the far side an ideal natural laboratory for studying impact processes and crustal evolution. Gravitational anomalies detected by orbiting spacecraft reveal hidden aspects of far side geology. Mass concentrations maskins beneath some far side basins indicate the presence of dense materials, possibly representing solidified impact melts or fragments of the impacting bodies themselves. These gravitational signatures provide insights into the three-dimensional structure of impact basins and the distribution of materials within the lunar interior. The mineralogical diversity of far side highland terrains reflects the complex processes of crustal formation and impact modification. Spectroscopic observations from orbit reveal variations in the abundance of different minerals, including anorthosite, nerite, and troctolite components of the lunar highland suite. These variations provide clues about the original differentiation of the lunar magma ocean and subsequent modification by impact processes. Cryptomere deposits ancient mare materials that have been covered by later highland ejecta may be more common on the far side than previously recognized. These buried volcanic deposits, detectable through careful analysis of surface compositions and gravitational anomalies, suggest that early volcanism may have been more extensive on the far side than the current surface expression indicates, with many ancient lava flows subsequently buried by impact debris. The thermal history of the far side can be inferred from the preservation state of ancient geological features and the distribution of different rock types. The lack of extensive volcanism suggests that the far side cooled more rapidly and completely than the near side, ceasing major geological activity early in lunar history. This early cessation of activity preserved the ancient impact record, while preventing the resurfacing that obscured early history. On the more geologically active near side, future sample return missions to the far side will provide ground truth for understanding these geological processes and testing theories developed from orbital observations. The South Pole Aitken Basin represents a particularly high-priority target for sample collection, as materials from this enormous impact structure could provide the first direct samples of lunar mantle rocks and resolve questions about the Moon's internal composition and differentiation. As we continue our exploration of the Moon's hidden face, we carry with us an appreciation for the far side's role as a geological time capsule that preserves evidence of processes that shaped not just the Moon, but all rocky planets during the solar system's violent youth. The strange geology of the far side reminds us that planetary evolution can follow dramatically different paths, even on the same world, creating hemispheres that tell different stories about cosmic history while remaining forever linked by their shared origin and destiny. Our peaceful journey now carries us to the most spectacular geological feature on the Moon's far side, the South Pole Aitken Basin, a colossal impact structure so vast and ancient that it represents one of the most significant events in lunar history and provides our best window into the Moon's deep interior structure. This enormous scar, stretching across nearly a quarter of the Moon's surface, tells the story of a cosmic collision so violent that it fundamentally altered the structure and evolution of our celestial companion. The South Pole Aitken Basin spans approximately 2,500 kilometers from rim to rim, making it not only the largest impact structure on the Moon, but one of the largest confirmed impact basins in the entire solar system. To appreciate its immense scale, imagine a crater large enough to stretch from New York to Denver, with a depth that excavated materials from more than 13 kilometers below the original surface. This tremendous size indicates that the impacting object was likely an asteroid or comet tens of kilometers in diameter, striking the Moon with energy equivalent to billions of nuclear weapons. The basin's elliptical shape and asymmetric structure provide clues about the impact event that created it. The elongated form suggests that the collision occurred at an oblique angle, rather than a direct vertical impact, with the impactor approaching from the northeast and striking the lunar surface at approximately 30 to 45 degrees from vertical. This oblique impact geometry explains the basin's extended dimensions and the complex pattern of ejecta distribution around its perimeter. The age of the South Pole Aitken Basin remains one of lunar science's most important chronological puzzles. Crater counting studies suggest that the basin formed between 4.2 and 4.3 billion years ago, making it one of the oldest recognizable surface features on the Moon. However, the exact timing has profound implications for understanding the late heavy bombardment, the period of intense impact activity that affected all inner solar system bodies during their early history. The basin's interior structure reveals the Moon's response to this catastrophic impact event. The tremendous collision excavated crustal materials and possibly exposed mantle rocks from depths never before accessible to study. The central portions of the basin show gravitational anomalies, consistent with dense materials brought up from the lunar interior, while the rim regions display the complex fractured and uplifted structures typical of large impact basins. One of the most scientifically valuable aspects of the South Pole Aitken Basin is its potential to provide samples of lunar mantle material. The impact that created the basin was so energetic that it may have excavated through the entire lunar crust in some regions, bringing mantle rocks to the surface, where they could eventually be collected by sample return missions. These deep materials would provide unprecedented insights into the Moon's internal composition and differentiation history. The mineralogical composition of the basin's interior differs significantly from typical lunar highland terrain, supporting the hypothesis that deep crustal or mantle materials have been exposed. Spectroscopic observations reveal higher concentrations of iron and magnesium-bearing minerals consistent with materials that formed at greater depths and higher temperatures than typical crustal rocks. These compositional signatures provide remote, sensing evidence for the excavation of deep materials during basin formation. The South Pole Aitken Basin's influence on lunar geology extends far beyond its immediate boundaries. The tremendous amount of material excavated during the impact event was distributed across the entire Moon, creating deposits of basin ejecta that can be detected on the near side and in equatorial regions. This global distribution of South Pole Aitken materials means that samples collected by Apollo missions may contain fragments derived from this ancient impact event. The basin's thermal evolution has been unique compared to other lunar regions due to the excavation of deep, potentially mantle-derived materials. These materials may have remained warm for extended periods after the impact, creating conditions that could have supported later volcanic activity or hydrothermal processes. The unusual composition of some materials within the basin may reflect chemical alteration that occurred during this extended cooling period. The preservation state of the South Pole Aitken Basin provides insights into the lunar cratering chronology and the decline of impact activity over geological time. Despite its great age, the basin's main structural features remain clearly visible, indicating that the rate of crater formation decreased significantly after the basin-forming event. This preservation supports models that place the end of the late heavy bombardment shortly after the basin's formation. The distribution of smaller craters within the South Pole Aitken Basin creates a complex stratigraphy that records the history of subsequent impact events. Some areas of the basin floor remain relatively smooth, preserving the original impact morphology, while other regions show dense concentrations of later craters that have modified the original structure. This variation in crater density provides insights into the temporal evolution of impact rates and the basin's exposure history. The South Pole Aitken Basin's location has important implications for future lunar exploration and resource utilization. The basin encompasses regions near the lunar South Pole where orbital dynamics and topographic effects create permanently shadowed areas that may contain deposits of water ice and other volatile compounds. These resources could prove essential for supporting human exploration and eventual permanent settlement of the lunar surface. The China National Space Administration's Chang'e mission made history in January 2019 by achieving the first successful landing within the South Pole Aitken Basin, specifically in Von Karman crater on the basin's floor. This mission provided the first direct surface investigations of basin materials and confirmed many of the compositional predictions made from orbital observations. The rover's measurements revealed the presence of materials consistent with excavated mantle rocks, mixed with impact melts and breccias. The gravitational field within the South Pole Aitken Basin shows complex patterns that reflect the basin's internal structure and the distribution of different rock types. Mass deficits in some regions indicate the presence of fractured or brecciated materials with lower than average density, while mass excesses in other areas suggest concentrations of dense rocks or impact melts. These gravitational signatures provide three-dimensional insights into the basin's internal architecture. The magnetic field characteristics of the South Pole Aitken Basin differ from surrounding highland regions, possibly reflecting the different rock types and formation processes within the basin. The impact event that created the basin occurred during an epoch when the Moon may have possessed a global magnetic field, and the shock and heating associated with the collision could have altered the magnetic properties of the affected rocks in complex ways. Scientific modeling of the South Pole Aitken Basin formation event has provided insights into the early impact environment of the inner solar system. Computer simulations of the collision reveal the tremendous energies involved and the complex sequence of excavation, uplift, and collapse that shaped the final basin structure. These models help scientists understand similar large impact basins on other planets and moons throughout the solar system. The South Pole Aitken Basin represents a natural laboratory for studying impact processes. Under lunar conditions, the basin's size and preservation state allow detailed investigation of phenomena that are poorly preserved or absent on more geologically active worlds like Earth. The complex relationships between impact energy, target properties, and resulting structure provide fundamental insights into planetary impact processes. Future exploration of the South Pole Aitken Basin will likely focus on sample return missions, designed to collect the potentially mantle-derived materials exposed within the basin. These samples would provide ground truth for theories about lunar internal structure and could resolve long-standing questions about the composition and differentiation of the moon's interior. Such missions would represent some of the most scientifically valuable lunar investigations possible with current technology. As we continue our exploration of the moon's Fascinates mysteries, we carry with us an appreciation for the South Pole Aitken Basin as both a window into the moon's violent past and a gateway to understanding the deep processes that shaped our celestial companion. This colossal structure reminds us that the moon preserves evidence of cosmic events so ancient and energetic that they fundamentally shaped the evolution of the entire Earth-Moon system, leaving scars that continue to reveal their secrets billions of years after the impacts that created them. As we drift deeper into the contemporary era of lunar exploration, we encounter the remarkable achievements of China's Chang'e program, a series of increasingly sophisticated missions that have revolutionized our understanding of the moon's facade and demonstrated new approaches to robotic exploration of our celestial companion. These missions, named after the Chinese goddess of the moon, represent humanity's return to active lunar exploration after decades of relative quiet, and have provided unprecedented insights into the hidden hemisphere that remained mysterious for so long. The Chang'e program began in 2007 with Chang'e 1, an orbital mission that provided comprehensive mapping of both lunar hemispheres and established China as the fifth nation to successfully reach the moon. This initial mission demonstrated China's growing space capabilities, while collecting scientific data about lunar topography, mineral composition, and the distribution of various elements across the surface. The success of Chang'e 1 paved the way for increasingly ambitious missions that would eventually achieve historic firsts in lunar exploration. Chang'e 2, launched in 2010, served as both a backup to the first mission and a technology demonstrator for future landing missions. This enhanced orbiter conducted high-resolution mapping of potential landing sites, while testing navigation and communication systems that would be essential for surface operations. After completing its lunar mission, Chang'e demonstrated extended operational capabilities by traveling to the Lagrange point and conducting a flyby of asteroid 4179 Tidal, showcasing the versatility of modern spacecraft design. The Chang'e 3 mission in 2013 marked China's first successful lunar landing, and the first soft landing on the moon since the Soviet Lunar 24 mission in 1976. The lander and its U-2 Jade Rabbit rover touched down in Mare Imbrium on the near side, conducting detailed surface investigations and demonstrating the technologies needed for future missions. While primarily focused on near-side exploration, Chang'e 3 provided valuable experience in lunar surface operations and validated systems that would be essential for the far-side missions to come. Chang'e 4 achieved a historic milestone in January 2019 by accomplishing the first successful landing on the moon's facade, touching down in Von Karman crater within the South Pole Aitken Basin. This achievement required unprecedented technical innovation, including the deployment of a relay satellite at the Lagrange point to maintain communication between the far side lander and Earth. The mission demonstrated that robotic exploration of the lunar far side was not only possible, but could be conducted with remarkable precision and scientific sophistication. The scientific objectives of Chang'e focused specifically on investigating the unique geological characteristics of the lunar far side. The mission's landing site within the South Pole Aitken Basin provided access to materials that may have been excavated from deep within the Moon during the basin-forming impact event. The lander and its U-2 rover carried instruments designed to analyze surface composition, subsurface structure, and the radio-astronomical environment of the far side. One of Chang'e's most significant discoveries involved confirming the presence of materials consistent with excavated mantle rocks within the South Pole Aitken Basin. Spectroscopic measurements revealed high concentrations of low-calcium pyroxene and olivine minerals typical of the lunar mantle but rare in crustal rocks. These findings provided the first direct surface confirmation that the basin-forming impact had indeed excavated materials from deep within the Moon, validating decades of theoretical modeling. The mission also conducted groundbreaking radio astronomy observations from the lunar far side, taking advantage of the natural radio-quiet environment created by the Moon's shielding of Earth's radio interference. The low-frequency spectrometer aboard the lander conducted the first astronomical observations from the lunar surface in radio frequencies that are blocked by Earth's ionosphere, opening a new window for studying the early universe and solar system radio emissions. Chang'e 4's biological experiments represented another first in lunar exploration, as the mission carried a small biosphere container with seeds and insects designed to study biological processes in the lunar environment. While the experiment was brief due to the extreme temperature variations during the lunar night, it demonstrated the potential for future biological research on the Moon and tested life support technologies that might be used in larger-scale experiments. The U-2 rover has demonstrated remarkable longevity and reliability in the harsh lunar environment, operating far beyond its designed lifetime and traveling significant distances across the far side surface. The rover's investigations have revealed the subsurface structure of the Von Karman crater through ground-penetrating radar measurements, showing a complex layered stratigraphy that records the history of impact events and material deposition within the South Pole Aitken Basin. The Chang'e 5T1 test mission in 2014 demonstrated the technologies needed for sample return operations by testing high-speed re-entry systems and recovery procedures. This mission served as a precursor to the Chang'e 5 sample return mission, validating the complex orbital mechanics and engineering systems required to collect lunar samples and return them safely to Earth for detailed laboratory analysis. Chang'e 5, successfully completed in December 2020, achieved China's first lunar sample return and the first new lunar samples delivered to Earth since the Soviet Lunar 24 mission in 1976. While this mission focused on near-side samples from Oceanus Procellarum, its success demonstrated the technical capabilities needed for future far-side sample return missions. The collected samples provided new insights into lunar volcanism and the timeline of geological processes. The Kuchao Relay satellite, deployed to support Chang'e for operations, demonstrated innovative approaches to far-side communication that will be essential for future exploration missions. Positioned at the Earth-Moon Lagrange point, the satellite provides continuous communication coverage for far-side operations, while also conducting its own scientific observations of radio emissions from space. This approach has become a model for future far-side exploration missions by other space agencies. International collaboration has been an important component of the Chang'e program, with instruments and scientific cooperation provided by partners including Germany, Sweden, the Netherlands, and Saudi Arabia. This collaborative approach has enhanced the scientific return of the missions, while demonstrating the global nature of lunar exploration and the benefits of international cooperation in space science. The Chang'e missions have also advanced our understanding of the lunar environment through detailed measurements of surface conditions, radiation levels, and the space environment around the Moon. These environmental characterizations are essential for planning future human missions and understanding the challenges that astronauts will face during extended operations on the lunar surface. Planned future Chang'e missions include ambitious sample return operations, targeting the lunar South Pole region, where permanently shadowed craters may contain deposits of water, ice, and other volatile compounds. These missions will build on the technological achievements of Chang'e 4 and 5, while addressing some of the most scientifically important questions about lunar resources and the history of water in the inner solar system. The success of the Chang'e program has inspired renewed international interest in lunar exploration, with multiple space agencies now planning or conducting their own lunar missions. The demonstration that sophisticated robotic exploration of the far side is technically feasible has opened new possibilities for scientific investigation and has contributed to the current renaissance in lunar exploration that includes missions from India, Japan, South Korea, and private companies. The technological innovations developed for the Chang'e missions have applications beyond lunar exploration, contributing to capabilities for deep space missions, asteroid exploration, and eventual human missions to Mars. The precision landing systems, autonomous navigation technologies, and long-duration surface operations demonstrated by these missions represent significant advances in robotic exploration capabilities as we continue our journey through the mysteries of the lunar far side. We carry with us appreciation for how the Chang'e program has transformed our understanding of the Moon's hidden hemisphere, while demonstrating new paradigms for robotic exploration. These missions have shown that the far side is not just a museum of ancient impacts, but an active frontier for scientific discovery, technological innovation, and international cooperation in exploring the cosmos. In the perpetual shadows of the Moon's polar regions where sunlight has not touched the surface for billions of years, lies one of the most remarkable discoveries in modern planetary science: vast deposits of water ice, preserved in conditions colder than Pluto's surface. These frozen treasures represent both a window into our solar system's ancient history and a revolutionary resource that could transform human space exploration. The lunar cold traps. The Moon's unique geometry creates the perfect conditions for these extraordinary ice deposits. Unlike Earth, which tilts 23.5 degrees and ensures sunlight eventually reaches every surface throughout the year, the Moon's rotational axis tilts only 1.5 degrees from vertical. This nearly upright stance creates permanently shadowed regions, PSs, in deep polar craters, where temperatures plummet below -230 degrees Celsius among the coldest places in our solar system. These regions act as cosmic cold traps, maintaining conditions so frigid that water molecules cannot escape once they arrive. When ancient comets and water-bearing asteroids impacted the Moon, throughout its 4.5 billion year history, water vapor from these impacts could migrate across the lunar surface through a process called hopping, temporarily entering the thin lunar atmosphere before settling back down until some molecules found their way into these eternal shadows where they became permanently frozen. The discovery journey, the story of lunar water ice detection, spans decades of increasingly sophisticated missions. It began unexpectedly in 1994 when the Clementine mission detected anomalous radar reflections from the South Polar region consistent with ice deposits. The Lunar Prospector mission followed with neutron spectroscopy that revealed hydrogen signatures near both poles, but these early observations remained tantalizingly inconclusive. Confirmation came through NASA's Lunar Reconnaissance Orbiter LRO, launched in 2009, which has spent over a decade mapping the Moon's surface with unprecedented precision. LRO's instruments confirmed water ice exists in numerous permanently shadowed craters near both poles, with some of the largest deposits found in the massive South Pole Aitken Basin. The most dramatic proof arrived with the LCRO-SS mission in 2009, which conducted a carefully orchestrated impact experiment. The mission deliberately crashed a spent rocket stage into Cabeus crater while a following spacecraft analyzed the debris plume. Spectroscopic analysis revealed clear evidence for water ice mixed into lunar soil, along with other volatile compounds including carbon monoxide, carbon dioxide, ammonia, and even trace amounts of silver and mercury. Distribution and characteristics. Recent analyses suggest billions of tons of water ice may be stored in permanently shadowed regions across the Moon, with concentrations ranging from a few percent to as much as 30% by mass in some locations. The distribution is far from uniform. The largest and most accessible deposits appear concentrated near the lunar South Pole, particularly in craters like Shackleton, Haworth, and Faustini. These locations have become prime targets for future landing sites because they offer both access to water ice and the possibility of extended sunlight periods on nearby crater rims for solar power generation. The ice doesn't exist as pure layers but is often intimately mixed with lunar soil to form ice-cemented regolith, which may actually be easier to extract and process than pure ice deposits. Origins across deep time. The water ice trapped in these permanent shadows tells a story spanning billions of years. Multiple delivery mechanisms have contributed to these deposits. Comets and asteroids impacting the Moon delivered water and volatile compounds, while solar wind interactions with oxygen-bearing lunar minerals may produce water molecules through chemical reactions. Some of these ancient water molecules may be among the oldest accessible materials in the inner solar system, preserving a record of the early bombardment period. Computer models suggest the efficiency of water trapping varies with crater size and depth, with larger, deeper craters generally accumulating more ice over geological time. However, the process isn't perfectly efficient. Cosmic ray bombardment and micrometeorite impacts can liberate water molecules, and some may be lost to space through sublimation and redistribution. Revolutionary implications. The discovery of extensive lunar water ice transforms the Moon from a barren, resource-poor destination into a potentially valuable staging ground for human expansion into the solar system. Water is not only essential for human survival, but represents one of the most precious resources in space. Through electrolysis, lunar water ice could be processed into hydrogen and oxygen, the fundamental components of rocket fuel, potentially making the Moon a refueling station for missions to Mars and beyond. Recent observations from NASA's SOFIA telescope have detected water molecules even in sunlit areas, like Clavius crater, suggesting the lunar water cycle may be more complex than previously understood, with water being produced, transported, and stored through various mechanisms across the entire lunar surface. Extracting and processing lunar water ice presents substantial but surmountable challenges. The extreme cold and permanent darkness require specialized equipment, capable of operating at temperatures that would freeze conventional systems. Proposed extraction methods range from simple heating systems that sublime ice directly into vapor, to sophisticated mining operations using focused sunlight redirected by mirrors, or nuclear-powered systems. The preservation and utilization of these deposits raises important questions about balancing scientific study with resource extraction. International cooperation through frameworks like the Artemis Accords will be crucial for ensuring these resources benefit all humanity while preserving the most scientifically valuable deposits. The study of lunar water ice reveals connections to other icy bodies throughout the solar system. Similar processes operate on Mercury, which despite its proximity to the Sun also harbors water ice in polar regions. The technologies being developed for lunar ice extraction could be adapted for Mars, where water ice exists at the poles and buried beneath the surface in many regions. As we continue studying these frozen archives hidden in eternal darkness, we're developing capabilities that will inform our approach to utilizing water resources throughout the solar system. The ancient ice trapped in lunar shadows represents a bridge between the cosmic past, when comets and asteroids shaped the inner solar system, and humanity's future among the stars. The patient accumulation of water ice over billions of years in the Moon's permanently shadowed regions demonstrates the vast timescales on which cosmic processes operate. While these deposits formed through countless small additions over eons, they may soon be accessed by human technology, marking our species' growing capability to understand and harness natural processes that have operated throughout solar system history. In these regions of eternal darkness, we find not emptiness, but abundance, ancient treasures waiting to fuel humanity's next great journey into the cosmos. As we continue our gentle exploration of our lunar companion, let us now turn our contemplative attention to the enduring mysteries and puzzling anomalies that have intrigued scientists for decades. Reminders that even our nearest celestial neighbor still holds secrets that challenge our understanding. There is something profoundly humbling about the realization that despite being the most studied celestial body beyond Earth itself, the Moon continues to present us with phenomena that defy easy explanation. These mysteries range from magnetic anomalies that shouldn't exist on a world without a global magnetic field, to unusual geological features that challenge our models of lunar formation, to unexplained observations that have puzzled astronomers since the earliest telescopic studies of our satellite. One of the most perplexing lunar mysteries involves the Moon's magnetic properties, or rather, the surprising remnants of ancient magnetism preserved in lunar rocks. Despite the Moon's lack of a current global magnetic field, when Apollo astronauts brought the first lunar samples back to Earth, scientists were startled to discover that many of these rocks showed evidence of having been exposed to strong magnetic fields, comparable in strength to Earth's current magnetic field. This discovery was deeply puzzling because the Moon today has no global magnetic field to speak of. Unlike Earth, which generates its magnetic field through the motion of liquid iron in its core, the Moon appears to lack the internal dynamics necessary to maintain a planetary magnetic field. Yet the evidence from lunar samples was undeniable. These rocks had been magnetized by exposure to powerful magnetic fields that once existed, but had somehow vanished. Recent research has proposed several possible explanations for this magnetic mystery, each more intriguing than the last. One theory suggests that the Moon once possessed a dynamo-generated magnetic field, similar to Earth's, powered by the cooling and solidification of its molten core. Computer models indicate that such a lunar dynamo could have operated for hundreds of millions of years after the Moon's formation, gradually weakening as the core cooled and solidified. Another hypothesis proposes that massive asteroid impacts could have temporarily generated intense magnetic fields through the interaction of impact-generated plasma with existing weak magnetic fields. These transient but powerful magnetic events could have magnetized surface rocks, even without a global dynamo. This theory gains support from the observation that some of the most strongly magnetized lunar regions correspond to areas opposite major impact basins, where the effects of massive impacts would have been focused. The magnetic mysteries extend beyond ancient magnetism to include localized magnetic anomalies that continue to puzzle lunar scientists. The Lunar Prospector and subsequent missions have mapped numerous magnetic swirls, strange patterns of enhanced magnetic field strength that often correspond to bright, sinuous markings visible on the lunar surface. These swirls appear to be associated with areas where the solar wind is partially deflected by local magnetic fields, creating complex patterns of space weathering and surface modification. The most famous of these magnetic swirls is the Reiner Gamma Formation on the Moon's near side, a bright, serpentine marking that has intrigued observers since its discovery. The magnetic field associated with this feature is strong enough to deflect solar wind particles, creating a natural mini-magnetosphere that protects the underlying surface from the darkening effects of space weathering. This protection results in the bright appearance that makes these features visible from Earth. What makes these magnetic anomalies particularly mysterious is their seemingly random distribution and unusual magnetic field configurations. Unlike the dipolar magnetic fields that characterize planets with active dynamos, lunar magnetic anomalies often show complex, multipolar field structures that are difficult to explain through any known geological process. Some researchers have proposed that these anomalies might be remnants of ancient magnetic fields that became frozen into the lunar crust as it cooled and solidified. Another enduring lunar mystery involves the asymmetric nature of our satellites to hemispheres. The Moon is tightly locked to Earth, always showing us the same face, but the hidden facade revealed by spacecraft missions turned out to be dramatically different from the familiar near side. While the near side is characterized by large, dark maria, ancient lava plains that fill impact basins, The far side is almost entirely covered by heavily cratered highland terrain. This hemispheric asymmetry extends beyond surface features to the Moon's internal structure. The lunar crust is significantly thicker on the far side, averaging about 68 kilometers compared to 60 kilometers on the near side. This crustal thickness difference affects the Moon's center of mass, which is offset from its geometric center toward the Earth-facing side. The reasons for this asymmetric structure remain debated, with theories ranging from the effects of Earth's gravity on the early Moon to asymmetric heating during the Moon's formation. The myriad themselves present mysteries beyond their asymmetric distribution. These vast lava plains formed billions of years ago when massive impacts breached the lunar crust and allowed molten rock from the interior to flow onto the surface. However, the timing and mechanism of maria formation remain incompletely understood. Most maria formed between 3.8 and 3.2 billion years ago during a period of intense bombardment. But why volcanic activity largely ceased after this time remains unclear. Some of the most intriguing lunar mysteries emerged from observations made by Apollo astronauts during their missions. Crews reported seeing unexplained lights on the lunar surface, particularly in regions where no obvious source of illumination should exist. These transient lunar phenomena have been reported by Earth-based observers for centuries, but the Apollo observations brought scientific credibility to reports of unusual lunar luminescence. The most famous of these observations occurred during Apollo 11, when astronauts Neil Armstrong and Buzz Aldrin reported seeing a strange glow on the horizon during their lunar surface activities. Similar observations were made during subsequent Apollo missions, with astronauts describing lights, flashes and glows that couldn't be easily explained by reflected sunlight or earthshine. While some of these observations have been attributed to outgassing from the lunar surface or impacts by micrometeorites, others remain unexplained. The Apollo missions also revealed acoustic mysteries that continue to puzzle scientists. During Apollo 10's orbit around the Moon, astronauts reported hearing strange space music, eerie sounds picked up by their radio equipment while passing behind the Moon and out of contact with Earth. The sounds, described as a combination of whistles and howls, lasted for nearly an hour and were recorded by the mission's communication systems. These mysterious sounds have since been attributed to interference between radio transmissions from the Apollo command and lunar modules, creating beat frequencies that produced the unusual audio patterns. However, the astronauts' initial reaction, their concern about whether to report the sounds to mission control, demonstrates how even experienced space travelers can encounter phenomena that challenge their understanding of the lunar environment. Recent Chinese missions to the Moon's far side have revealed new mysteries and confirmed some old ones. The Chang'e mission, which achieved the first soft landing on the lunar far side, has provided detailed observations of this previously inaccessible region. The mission has confirmed the unusual geological characteristics of the far side and revealed new details about the composition and structure of the lunar interior. Through seismic monitoring, one of the most significant discoveries from Chang'e 4 involves the detection of materials that appear to have originated from the Moon's mantle, brought to the surface by the massive impact that created the South Pole Aitken Basin. These materials have compositions unlike anything found in near-side samples, providing new insights into the Moon's internal structure, while raising new questions about the processes that shaped our satellite's formation and evolution. The Chang'e missions have also contributed to the mystery of lunar subsurface structures. Ground-penetrating radar observations have revealed complex layered structures beneath the lunar surface, some extending to depths of several hundred meters. These subsurface features appear to be related to ancient impact events and volcanic processes, but their exact nature and formation mechanisms remain subjects of ongoing research. Another class of lunar mysteries involves the Moon's tenuous atmosphere, or exosphere, which consists of individual atoms and molecules rather than the dense gas mixtures that characterize planetary atmospheres. This exosphere exhibits unexplained variations in density and composition that change with lunar day and night, solar activity, and seasonal variations in the Moon's orbit around Earth. observations have detected sodium, potassium, and other elements in the lunar exosphere, presumably released from the surface by solar wind bombardment and micrometeorite impacts. However, the processes that control the exosphere's behavior are not fully understood, and some observations don't match theoretical predictions. The discovery of water molecules in the exosphere has added another layer of complexity to these atmospheric mysteries. The Moon's interaction with Earth's magnetosphere also presents ongoing puzzles. When the Moon passes through Earth's magnetic tail, the extended portion of our planet's magnetic field that stretches away from the Sun, it experiences changes in its local space environment that affect surface charging and the behavior of dust particles. Some observations suggest that lunar dust may become electrostatically charged and levitate during these passages, though the exact mechanisms remain debated. Long-term observations of the Moon have revealed subtle changes that challenge our understanding of lunar surface processes. Some craters appear to have undergone modifications over historical times. Cales, with changes in their appearance documented through telescopic observations spanning several centuries. While most of these changes can be attributed to lighting effects and observational improvements, some appear to reflect actual surface modifications whose causes remain unclear. The mystery of lunar dust behavior continues to puzzle scientists and engineers planning future missions. Apollo astronauts reported that lunar dust had unusual properties. It was extremely fine, clingy, and abrasive, adhering to spacesuits and equipment in ways that couldn't be fully explained by electrostatic charging alone. Understanding the behavior of lunar dust is crucial for designing equipment and habitats for future lunar missions. Modern theoretical models of lunar dust behavior suggest that complex interactions between solar radiation, the solar wind, and the Moon's surface charge create dynamic dust environments that vary with location and time. Some models predict that dust particles could become suspended above the lunar surface, creating clouds or fountains of levitating material. However, direct observations of such phenomena remain elusive. The mystery of lunar formation itself continues to evolve as new evidence emerges from sample analysis and theoretical modeling. While the giant impact hypothesis, the idea that the Moon formed from debris created when a Mars-sized object collided with early Earth, has gained widespread acceptance, many details of this process remain unclear. Questions about the impactor's composition, the dynamics of the collision, and the subsequent formation of the Moon continue to challenge scientists. Recent isotopic analyses of lunar samples have revealed subtle but significant differences from Earth materials, suggesting that the Moon-forming impact may have been more complex than initially thought. These findings have led to refined models of lunar formation that invoke multiple impacts, different impactor compositions, or alternative formation mechanisms that could explain the observed isotopic signatures. As we drift peacefully through contemplation of these lunar mysteries, we can appreciate how they remind us that scientific understanding is always evolving. Each new mission, each advanced analysis technique, and each theoretical breakthrough reveals new aspects of our Moon's complex nature, while often raising new questions about phenomena we thought we understood. The enduring mysteries of our lunar companion serve as a reminder that exploration and discovery are ongoing processes, even for the most familiar and well-studied celestial bodies. New observations can reveal unexpected phenomena that challenge our assumptions and expand our understanding. These mysteries inspire continued exploration and research, driving the development of new technologies and techniques for studying not just the Moon, but other worlds throughout the solar system. In the gentle contemplation of these lunar enigmas, we find both humility and inspiration. Humility in recognizing how much we still have to learn about our nearest neighbor, and inspiration in the knowledge that each mystery solved opens new avenues for understanding the complex processes that shape planets and moons throughout the cosmos. The Moon's secrets, revealed gradually through patient observation and analysis, remind us that the universe continues to surprise us with phenomena beyond our current comprehension, encouraging us to maintain our sense of wonder and curiosity about the cosmic environment we are only beginning to explore and understand. As we continue our peaceful journey through lunar science, let us now contemplate one of the most dramatic events in our solar system's history, the catastrophic collision that gave birth to our moon through violence so profound it reshaped the early Earth and created the celestial companion that has watched over our planet. For more than 4 billion years, there is something both terrifying and beautiful about imagining the cosmic violence that created our serene moon. The giant impact hypothesis describes an event of almost unimaginable scale, a Mars-sized world which scientists have named Thea after the Greek Titaness, who gave birth to the moon goddess Selene, striking the early Earth with such tremendous force that it vaporized rock, created a global magma ocean, and hurled enough material into orbit to eventually coalesce into our lunar companion. This theory of violent lunar birth represents one of the greatest detective stories in planetary science, pieced together from clues scattered across Apollo samples, computer simulations, and our growing understanding of how planetary systems form and evolve. The evidence for this cosmic catastrophe is written in the very rocks beneath our feet, and in the samples brought back from the moon by brave astronauts more than half a century ago. The story begins in the early solar system, about 4.5 billion years ago, when our planetary neighborhood was a far more chaotic place than the relatively stable system we know today. The planets were still forming through the violent process of accretion, as countless planetesimals, rocky building blocks ranging from pebbles to mountain-sized objects, collided and merged to build the worlds we see today. In this primordial environment, massive impacts were common events that shaped the formation and evolution of every terrestrial planet. The early Earth was very different from our modern world. It was smaller, hotter, and surrounded by a disk of debris left over from the planet's formation. The atmosphere was likely composed of hydrogen and helium captured from the solar nebula, along with gases released by volcanic activity and impacts. This early Earth rotated much faster than today, with days lasting only 5 to 6 hours, and it lacked the stabilizing influence of a large moon to moderate its axial tilt and climate. According to the giant impact hypothesis, approximately 50 to 100 million years after Earth's initial formation, our planet encountered Thea, a Mars-sized protoplanet that had been following a similar orbit around the young Sun. Computer simulations suggest that Thea was roughly half the size of Earth, with a mass comparable to Mars, and that it approached our planet at a relatively low velocity, perhaps 4 to 15 kilometers per second, slow by cosmic impact standards but still carrying tremendous kinetic energy. The collision itself would have been an event of indescribable violence. When Thea struck the Earth, the impact energy was equivalent to billions of hydrogen bombs exploding simultaneously. The collision occurred at an oblique angle rather than head-on, which was crucial for the moon's formation. A direct impact would have completely shattered both worlds, while a glancing blow allowed some of the material to be ejected into orbit around the surviving, enlarged Earth. The immediate aftermath of this cosmic collision transformed both worlds beyond recognition. The impact vaporized enormous amounts of rock and metal, creating temperatures of thousands of degrees Celsius and pressures millions of times greater than Earth's surface pressure today. Much of both Earth and Thea was reduced to superheated gas and liquid rock, with the lighter silicate materials being preferentially ejected into space, while the denser iron cores merged to form Earth's enlarged core. The debris thrown into orbit around Earth by this impact formed a disk of vaporized and molten rock that extended from just above Earth's surface to several times the Earth's radius. This circumterrestrial disk was incredibly hot and dense, glowing like a star and radiating enormous amounts of thermal energy into space. Computer models suggest that the disk contained roughly twice the mass of the current moon, indicating that much of the initial debris either fell back to Earth or was lost to space. During the moon's formation process, the formation of the moon from this impact-generated debris disk required approximately 1,000 years, remarkably fast by geological standards but still involving complex processes of cooling, condensation and gravitational accretion. As the disk cooled, the vaporized rock began to condense into liquid droplets and eventually solid particles. These particles then began to clump together under their mutual gravitational attraction, gradually building larger and larger bodies through the same accretion processes that had formed the planets themselves. The early moon that emerged from this process was very different from the world we see today. It formed much closer to Earth, perhaps only 15,000 to 20,000 kilometers away, roughly 20 times closer than its current distance of 380 for 1,000 kilometers. At this close range, the moon would have appeared enormous in Earth's sky, subtending an angular diameter of 10 to 15 degrees, 20 to 30 times larger than the moon appears today. The gravitational interactions between Earth and this nearby moon would have been tremendously powerful, creating massive tidal forces that shaped both worlds' early evolution. The newly formed moon was also completely molten, covered by a global magma ocean hundreds of kilometers deep. This lunar magma ocean began cooling and crystallizing from the bottom up, with denser minerals sinking to form the moon's mantle and crust, while lighter materials floated to the surface. The crystallization of this magma ocean took tens of millions of years, and established the fundamental structure of the moon's interior that persists today. Evidence for the giant impact hypothesis comes from multiple lines of investigation that have strengthened the theory over several decades of research. The most compelling evidence comes from the isotopic composition of lunar samples, which show that Earth and Moon rocks have nearly identical ratios of oxygen isotopes. This isotopic similarity suggests that Earth and Moon materials were thoroughly mixed during the impact event, which would be expected if both worlds were largely vaporized and their materials combined in the circumterrestrial debris disk. The Moon's small iron core, which comprises only about 2% of its total mass compared to Earth's 32% iron core, also supports the impact hypothesis. The collision models predict that most of Thea's iron core would have merged with Earth's core, while the ejected material that formed the Moon would have been preferentially enriched in silicate rock from both worlds' mantles. This explains why the Moon is so depleted in iron and other metallic elements compared to Earth. The angular momentum of the Earth-Moon system provides additional evidence for the impact theory. The current orbital motion of the Moon and the rotation of the Earth together contain angular momentum that matches predictions from impact simulations. The collision would have imparted tremendous rotational energy to the Earth-Moon system, explaining both Earth's initial rapid rotation and the Moon's orbital motion. Recent advances in computer modeling have refined our understanding of the impact event and its aftermath. High-resolution simulations using sophisticated physics models have revealed that the collision was even more complex than initially thought. Rather than a simple merger, the impact appears to have involved multiple phases of collision, separation, and re-impact as gravitational forces pulled the disrupted worlds back together. These detailed simulations suggest that Thea did not simply merge with Earth, but may have partially survived the initial collision, existing as a separate, heavily damaged world for several hours before the two bodies finally coalesced. During this chaotic period, material from both worlds was repeatedly exchanged, explaining the thorough mixing of Earth and lunar materials revealed by isotopic analyses. The isotopic evidence has also revealed subtle but significant differences between Earth and Moon that have led to refinements in the impact theory. While the oxygen isotopes are nearly identical, other elements show small but measurable differences that suggest the Moon may have incorporated slightly more Thea material than initially predicted. These findings have led to modified impact scenarios involving higher energy collisions or multiple impact events. One of the most intriguing recent developments in lunar formation theory involves the possibility that Earth may still harbor remnants of Thea within its interior. Seismic studies of Earth's deep mantle have revealed large, dense regions beneath Africa and the Pacific Ocean that have different properties from the surrounding mantle rock. Some researchers have proposed that these anomalous regions, known as large low shear velocity provinces, might be fragments of Thea's mantle that never fully mixed with Earth's interior. During the impact event, the giant impact hypothesis also helps explain several unique characteristics of the Earth-Moon system that distinguish it from other planet-satellite pairs in the solar system. The Moon is unusually large relative to Earth. Our satellite has about 1/81st the mass of Earth, while most moons are much smaller compared to their parent planets. This large mass ratio, along with the system's high total angular momentum, is naturally explained by the impact scenario. The theory also explains the moon's orbital characteristics, including its slight inclination relative to Earth's equatorial plane and its gradually increasing distance from Earth. The impact would have initially placed the moon in an equatorial orbit, but subsequent gravitational interactions with the Sun have gradually tilted the lunar orbit to its current inclination of about 5 degrees. Studies of other planetary systems have revealed that giant impacts were likely common during the late stages of terrestrial planet formation. Evidence for similar collisions has been found throughout the solar system, from Mercury's unusually large core possibly the result of a giant impact that stripped away much of its mantle, to the tilted rotation axis of Uranus which may have been knocked over by a massive collision. These observations support the idea that the moon-forming impact was not a unique event, but rather a typical outcome of the violent planet formation process. The timing of the lunar-forming impact has important implications. For the early evolution of life on Earth, the collision would have sterilized Earth's surface and atmosphere, vaporizing any oceans that might have existed and creating conditions hostile to any primitive life forms. This suggests that life on Earth could not have begun until after the moon-forming impact, providing constraints on when biological processes first emerged on our planet. The impact also had profound effects on Earth's subsequent geological evolution. The collision added substantial mass to Earth, increased its internal heat content, and may have initiated the plate tectonic processes that continue to shape our planet's surface today. Some researchers have suggested that the impact provided the energy needed to kickstart mantle, convection and plate tectonics, processes that have been crucial for maintaining Earth's habitability over geological time. Modern research continues to refine our understanding of the moon-forming impact through improved computer simulations, more precise isotopic analyses, and comparative studies of other planetary systems. New techniques for analyzing lunar samples at the atomic level are revealing additional details about the impact event and the subsequent evolution of both Earth and Moon. The discovery of exoplanets on other stars has provided additional context for understanding giant impacts and their role in planetary system evolution. Observations of young stellar systems have revealed debris disks and other evidence of ongoing planet formation, including what appear to be recent giant impacts around nearby stars. These observations help validate our understanding of the processes that shaped our own solar system billions of years ago. As we drift peacefully through contemplation of this violent cosmic event, we can appreciate the profound irony that our serene, stabilizing moon was born from one of the most catastrophic collisions in our solar system's history. The giant impact that created our lunar companion represents a perfect example of how destruction and creation are intimately linked in cosmic evolution, with violent events often leading to new structures and possibilities. The moon that emerged from this cosmic violence has profoundly influenced Earth's subsequent evolution, stabilizing our planet's axial tilt and creating the tidal forces that may have aided the development of life. In this sense, the catastrophic impact that created our moon also helped create the stable conditions that allowed complex life to evolve and flourish on Earth, demonstrating the interconnected nature of cosmic processes and their long-term consequences for planetary habitability. The gentle presence of our moon in Earth's sky serves as a constant reminder of this ancient violence, now transformed into a source of beauty, inspiration, and scientific wonder that continues to shape our understanding of how worlds are born and how planetary systems evolve through cosmic time. As we continue our contemplative journey around our lunar companion, let us now drift toward the moon's hidden hemisphere, the mysterious far side that remained unknown to humanity until the space age, where the most pristine radio environment in the inner solar system offers unprecedented opportunities for listening to the cosmos. There is something profoundly peaceful about contemplating the moon's far side, that hemisphere which never faces Earth due to tidal locking, where the absence of our planet's radio chatter creates a cosmic sanctuary of electromagnetic silence. This radio-quiet environment represents one of the most valuable natural resources in our solar system, a place where sensitive radio telescopes could detect the faintest whispers from the early universe without interference from the cacophony of human technology. The far side of the Moon remained completely hidden from human view until October 7, 1959, when the Soviet Lunar 3 spacecraft swung around the Moon and captured the first blurry images of this alien landscape. Those early photographs revealed a world dramatically different from the familiar near side, heavily cratered, and lacking the large, dark maria that characterized the face of the Moon we see from Earth. More importantly for astronomy, this hidden hemisphere offered something that exists nowhere else in the inner solar system: complete radio silence from Earth. Understanding the unique value of the lunar side for radio astronomy requires appreciating the electromagnetic environment of modern Earth. Our planet is surrounded by an ever-growing bubble of radio emissions from billions of electronic devices, radio and television transmitters, radar systems, satellites, and countless other sources of electromagnetic radiation. This radio frequency interference makes it increasingly difficult for Earth-based radio telescopes to detect weak signals from space, particularly at low frequencies where some of the most interesting cosmic phenomena occur. The Moon acts as a natural shield, blocking all radio emissions from Earth and creating what astronomers call a radio shadow on its facade. This shielding is complete and permanent. At radio wavelengths, the Moon is essentially opaque, so no terrestrial radio signals can reach the far-side hemisphere. This creates an environment of electromagnetic quietude that is unmatched anywhere else in the accessible solar system, making it an ideal location for radio astronomy observations that would be impossible from Earth. The scientific potential of lunar far-side radio astronomy is extraordinary. Radio telescopes operating in this protected environment could detect signals that are completely overwhelmed by interference when observed from Earth. These include the extremely faint radio emissions from the cosmic dark ages, the period between the end of cosmic recombination about 400,000 years after the Big Bang, and the formation of the first stars and galaxies hundreds of millions of years later. During the cosmic dark ages, the universe was filled with neutral hydrogen gas that gradually cooled and settled into increasingly complex structures under the influence of dark matter. This process should have left subtle radio signatures at a wavelength of 21 centimeters, the characteristic emission line of neutral hydrogen, that have been redshifted to much longer wavelengths by the expansion of the universe. Detecting these ancient signals would provide unprecedented insights into the formation of the first cosmic structures and the transition from the Dark Ages to the era of star formation. The challenges of detecting these primordial signals from Earth are almost insurmountable. The expected signals are incredibly weak, perhaps 1,000,000 times fainter than the cosmic microwave background radiation, and they occur at frequencies that are heavily contaminated by human-generated radio interference. Even the most sensitive Earth-based radio telescopes, located in the most remote radio-quiet zones, cannot escape the growing blanket of electromagnetic pollution that surrounds our planet. Chang'e 4, China's pioneering far-side lunar mission, has provided our first direct experience with radio astronomy from the Moon's hidden hemisphere. The mission carries a low-frequency radio spectrometer designed to study the radio environment and test the feasibility of astronomical observations from this unique vantage point. The early results have confirmed the exceptional radio quietude of the far side, while also revealing some unexpected complexities in the lunar electromagnetic environment. One of the most significant discoveries from Chang'e 4's radio observations is that even the far side of the Moon is not completely free from radio interference. So the radio bursts, galactic background radiation, and emissions from Jupiter create a natural radio background that must be accounted for in astronomical observations. However, these natural sources are relatively weak and well understood compared to the chaotic mix of artificial signals that plague Earth-based radio telescopes. The mission has also revealed that the lunar surface itself can influence radio observations in subtle ways. The electrical properties of lunar soil and rock can affect how radio waves propagate and reflect, creating local variations in the radio environment that must be understood and calibrated. Additionally, the interaction between the solar wind and the Moon's surface can generate weak radio emissions that could potentially interfere with sensitive astronomical observations. Despite these challenges, the radio environment on the Moon's far side remains orders of magnitude quieter than anywhere accessible on Earth. This has led to numerous proposals for constructive large-scale radio telescope arrays that could take advantage of this unique environment to explore cosmic phenomena that are currently beyond our observational reach. One of the most ambitious concepts is the proposed Lunar Crater Radio Telescope, which would construct a massive radio dish within a large crater on the far side. This telescope could potentially have a diameter of several kilometers, making it the largest radio telescope ever built. The natural bowl shape of lunar craters provides an ideal foundation for such an instrument, and the Moon's low gravity and lack of atmosphere would simplify construction compared to building similar facilities on Earth. The far-view concept represents another approach to lunar radio astronomy, proposing to construct an array of thousands of small radio antennas distributed across the far-side surface. These antennas would work together as an interferometer, providing extremely high resolution and sensitivity for radio astronomical observations. The array could be manufactured using materials extracted from the lunar surface, making it a sustainable and expandable astronomical facility. The scientific goals of lunar far-side radio astronomy extend far beyond studying the cosmic dark ages. Such facilities could search for extraterrestrial intelligence with unprecedented sensitivity, detecting artificial radio signals from technological civilizations around nearby stars. The radio-quiet environment would allow the detection of much weaker signals than possible from Earth, potentially extending the range of SETI searches to thousands of nearby star systems. Lunar radio telescopes could also study the radio emissions from exoplanets, particularly the strong radio bursts that some planets are expected to produce through interactions between their magnetic fields and their host stars. These planetary radio signals are too weak to detect reliably from Earth, but might be accessible to sensitive instruments operating in the Moon's radio shadow. The study of cosmic magnetic fields represents another major scientific opportunity for lunar radio astronomy. Many cosmic phenomena, from stellar formation regions to galaxy clusters, produce synchrotron radiation that can only be observed at radio wavelengths. The enhanced sensitivity of lunar radio telescopes could reveal new details about magnetic field structures throughout the universe, providing insights into fundamental physical processes that shape cosmic evolution. Solar and heliospheric physics could also benefit enormously from lunar far-side radio observations. The Moon's location outside Earth's magnetosphere provides a unique vantage point for studying solar radio emissions and their propagation through the solar wind. Such observations could improve our understanding of space weather and its effects on planetary environments throughout the solar system. The technical challenges of implementing radio astronomy on the Moon's far side are substantial, but not insurmountable. The extreme temperature variations, from over 120 Celsius in sunlight to below -170 Celsius in shadow, require robust electronic systems and thermal management. The lack of atmosphere means that equipment must be protected from micrometeorite impacts and the effects of unfiltered solar radiation. Power systems for lunar radio telescopes present particular challenges, as solar panels are only effective during the 2-week lunar day, requiring massive battery systems or alternative power sources to maintain operations during the equally long lunar night. Nuclear power systems offer one solution, providing continuous power independent of solar illumination, while also supplying heat to keep sensitive electronics warm during the bitter lunar night. Communication with Earth-based control centers is another significant challenge. For far-side operations, direct communication is impossible due to the Moon's bulk-blocking radio signals, requiring relay satellites in lunar orbit or at the Earth-Moon Lagrange points to maintain contact. This communication delay and bandwidth limitation affects how such telescopes could be operated and controlled. International cooperation will be essential for realizing the full potential of lunar far-side radio astronomy. The scale and cost of proposed telescope arrays exceed what any single nation or space agency could reasonably undertake alone. While the scientific benefits would be shared by the global astronomy community, the establishment of international protocols for protecting the radio environment of the far side will also be crucial to prevent future activities from compromising this unique natural resource. The Outer Space Treaty and other international agreements provide some framework for managing lunar resources, but additional protocols may be needed to specifically protect the radio-quiet environment of the far side. As commercial space activities expand and more nations develop lunar capabilities, the pressure to use all parts of the Moon for various purposes will grow, potentially threatening the pristine electromagnetic environment that makes far-side radio astronomy possible. Recent proposals have suggested establishing formal radio-quiet zones on the Moon, similar to the radio astronomy protection zones that exist around major Earth-based telescopes. These zones would restrict activities that could generate radio frequency interference, preserving the far side's unique value for astronomical observations, while allowing other uses of lunar resources in appropriate locations. The development of lunar far-side radio astronomy will also drive advances in autonomous systems and robotic technology. The communication delays and harsh environment mean that telescope systems must operate with minimal human intervention, automatically adjusting their observations and maintaining themselves over long periods. These technological developments will benefit not only astronomy, but also future robotic exploration throughout the solar system. Looking toward the future, the establishment of radio telescopes on the Moon's far side represents a natural progression in humanity's quest to understand the cosmos, just as the development of space-based optical telescopes like Hubble and Webb has revolutionized our view of the universe by escaping Earth's atmospheric limitations. Lunar radio telescopes could provide our first clear view of cosmic phenomena that remain hidden behind the growing veil of terrestrial radio interference. The Moon's far side offers more than just radio silence. It provides a stable platform with low gravity, no atmosphere, and minimal seismic activity, creating ideal conditions for precision radio astronomy. The absence of ionospheric disturbances and weather means that observations can continue uninterrupted for weeks or months at a time, accumulating the long integration times necessary to detect extremely weak signals from the distant universe. As we contemplate the peaceful radio silence of the Moon's far side, we can appreciate both its scientific value and its symbolic significance. This electromagnetic sanctuary represents one of the last pristine environments in the inner solar system, a place where we can still listen to the universe without the interference of our own technological civilization. The radio telescopes that may one day populate this hidden hemisphere will serve as our ears to the cosmos, allowing us to hear the faint whispers of cosmic evolution that are drowned out by the noise of our modern world. The vision of vast radio telescope arrays spread across the lunar far side, their antennas silently listening to signals from the early universe and distant civilizations, captures the profound beauty of scientific exploration. In the perpetual radio silence of the Moon's hidden hemisphere, humanity may finally be able to hear the cosmic symphony that has been playing since the dawn of time, adding new harmonies to our understanding of existence itself and our place within the vast orchestra of the universe. As we continue our gentle drift through lunar science, let us now turn our contemplative attention toward the future, where humanity stands on the threshold of returning to the Moon not as visitors, but as permanent residents, establishing the first extraterrestrial settlements that will serve as stepping stones to the stars. There is something profoundly moving about contemplating humanity's return to the Moon. After more than half a century of absence, the Apollo missions demonstrated that humans could travel to our lunar companion, walk on its surface, and safely return to Earth. But those heroic expeditions were brief visits to an alien world. The future missions now being planned represent something far more ambitious: the establishment of permanent human presence on the Moon, creating self-sustaining communities that will transform our relationship with our celestial neighbor. The Artemis program, NASA's ambitious initiative to return humans to the Moon, embodies this new vision of sustainable lunar exploration. Unlike the Apollo program, which focused on demonstrating American technological superiority during the Cold War, Artemis aims to establish a permanent human presence on the Moon that will enable scientific discovery, economic development, and the eventual expansion of human civilization beyond Earth. Artemis 2, currently scheduled for launch no earlier than April 2026, will carry for astronauts around the Moon in the first crewed lunar mission since Apollo 17 in 1972. This mission will test the Orion spacecraft and Space Launch System rocket in the demanding environment of deep space, while providing astronauts with crucial experience in lunar operations. The mission will not land on the Moon, but will serve as a crucial stepping stone toward the surface missions that will follow. Artemis 3, planned for mid-2027, aims to land the first humans on the Moon's south polar region, where abundant water ice deposits offer the potential for sustainable resource utilization. This mission will mark several historic milestones. It will include the first woman and first person of color to walk on the lunar surface, and it will establish humanity's first foothold in a region of the Moon that offers both scientific interest and practical resources for future development. The choice of the lunar South Pole as the target for renewed human exploration reflects decades of scientific discovery and technological planning. This region offers access to permanently shadowed craters containing water ice, while nearby crater rims experience extended periods of sunlight that could power solar arrays and provide thermal stability for human habitats. The combination of water resources and solar power makes the South Polar region ideal for establishing permanent human settlements. The Lunar Gateway, a small space station that will orbit the Moon, represents a crucial component of the Artemis architecture. This facility will serve as a staging area for lunar surface operations, a research laboratory for studying the lunar environment, and a testing ground for technologies needed for future Mars missions. The Gateway will be assembled in pieces beginning in the late 2020s, creating humanity's first permanent outpost in the vicinity of the Moon. Beyond the initial Artemis missions, NASA envisions the gradual development of a permanent lunar base camp that could support extended human presence on the Moon's surface. This base would begin as a simple shelter and basic life support systems, gradually expanding to include laboratories, workshops, resource processing facilities, and eventually full-scale industrial capabilities. The base would be supplied initially by cargo missions from Earth, but would gradually become more self-sufficient through the utilization of lunar resources. The concept of lunar resource utilization, often called in situ resource utilization or ISRU, is central to plans for permanent lunar settlement. The Moon offers numerous resources that could support human activities, including water ice for drinking water and rocket fuel production, silicon and metals for construction materials, and helium-3 deposited by the solar wind that could potentially fuel future fusion reactors. Learning to extract and process these materials will be essential for establishing truly sustainable lunar communities. Water ice extraction represents the most immediate and crucial aspect of lunar resource utilization. The permanently shadowed regions near the lunar poles contain billions of tons of water ice that could be harvested using heating systems, excavation equipment, and processing facilities. The extracted water could be consumed directly, used for radiation shielding, or split into hydrogen and oxygen to create rocket propellant for missions throughout the solar system. The challenges of establishing permanent human presence on the Moon are substantial and multifaceted. The lunar environment is extraordinarily hostile to human life, with no atmosphere, extreme temperature variations, intense radiation, and a constant threat of micrometeorite impacts. Every system designed for lunar operations must be robust, reliable, and capable of operating in conditions that would quickly destroy conventional Earth-based equipment. Radiation protection represents one of the most serious challenges for lunar settlement. Unlike Earth, which is protected by a magnetic field and dense atmosphere, the Moon offers no natural shielding from cosmic rays and solar particle events. Future lunar habitats will need to incorporate sophisticated radiation protection systems, possibly including underground construction, water-filled shielding walls, or electromagnetic deflection systems to protect human inhabitants. The psychological challenges of lunar settlement may prove as difficult as the physical ones. Future lunar residents will live in isolated, confined environments with no possibility of quick return to Earth. The lunar day-night cycle of nearly a month, the alien landscape, and the constant awareness of the hostile environment beyond the habitat walls will create psychological stresses that must be carefully managed. Through habitat design, communication systems, and recreational activities, international cooperation is becoming increasingly important in lunar exploration, with multiple nations and space agencies contributing to future missions and base development. The Artemis Accords, signed by numerous countries, establish principles for peaceful lunar exploration and resource utilization that could serve as the foundation for international lunar settlements. These agreements address issues ranging from scientific data sharing to the prevention of harmful interference between different nations' lunar activities. Commercial space companies are playing increasingly important roles in lunar exploration and development. Companies like SpaceX, Blue Origin, and others are developing lunar landers, cargo delivery systems, and life support technologies that will be essential for establishing permanent human presence on the Moon. This commercial involvement promises to reduce costs and accelerate the timeline for lunar settlement while creating new economic opportunities in space. The development of lunar infrastructure will require unprecedented levels of automation and robotics. Much of the initial base construction, resource extraction, and facility maintenance will need to be performed by robotic systems, operating with minimal human oversight. These robots must be capable of complex manipulation tasks, problem-solving, and self-repair in the harsh lunar environment. 3D printing and additive manufacturing technologies are expected to play crucial roles in lunar base development, rather than transporting all necessary equipment and structures from Earth. Future missions will carry compact 3D printers capable of creating tools, spare parts, and even structural components using lunar materials. This approach could dramatically reduce the cost and complexity of lunar operations while providing greater flexibility and self-sufficiency. The timeline for establishing permanent lunar bases extends well beyond the initial Artemis missions. Current plans envision a gradual build-up of capabilities throughout the 2030s and 2040s, with small research stations evolving into larger settlements capable of supporting hundreds, or eventually thousands of residents. These communities would serve multiple purposes: scientific research, resource extraction, technology development, and preparation for missions to Mars and beyond. Lunar agriculture represents another crucial aspect of long-term lunar settlement. Growing food on the Moon will require sophisticated closed-loop life support systems that recycle air, water, and nutrients with near-perfect efficiency. Research on the International Space Station and in analog facilities on Earth is developing the technologies needed to grow crops in the confined, controlled environments that will characterize lunar habitats. The economic justification for lunar settlement remains a subject of ongoing debate and development. While the initial costs of establishing lunar bases will be enormous, proponents argue that the Moon's resources, particularly rare materials like helium-3 and platinum group metals, could eventually justify the investment. Additionally, the Moon could serve as a manufacturing and refueling hub for activities throughout the solar system, reducing the costs of missions to Mars and the outer planets. Educational and research opportunities on the Moon could also provide economic and scientific justification for permanent settlement. Lunar universities and research institutes could conduct studies impossible on Earth, from low-gravity manufacturing to astronomical observations, to geological investigations of lunar formation and evolution. These facilities could attract researchers from around the world while training the next generation of space explorers and scientists. The development of lunar tourism represents another potential economic driver for lunar settlement. As transportation costs decrease and safety systems improve, the Moon could become accessible to wealthy tourists seeking the ultimate adventure travel experience. Lunar hotels, recreation facilities, and adventure tours could provide revenue streams to support the infrastructure needed for scientific and industrial activities, medical facilities, and healthcare. Systems for lunar residents will require significant innovation and preparation. The low-gravity environment, radiation exposure, and isolation from Earth will create unique health challenges that must be addressed through advanced medical technology, telemedicine systems, and possibly surgical robots capable of operating without human supervision. Emergency medical evacuation to Earth may not always be possible, requiring lunar medical facilities to handle serious injuries and illnesses independently. The cultural and social aspects of lunar settlement will be as important as the technical challenges. Future lunar communities will need to develop their own social structures, governance systems, and cultural traditions adapted to the unique environment and challenges of life on the Moon. These communities may eventually develop distinct identities separate from their Earth origins, becoming the first truly extraterrestrial human cultures. Environmental protection and sustainability will be crucial considerations for lunar settlement development, while the Moon lacks the complex ecosystems that must be protected on Earth. Lunar activities could still have significant environmental impacts, from contamination of scientifically valuable sites to disruption of the pristine conditions needed for astronomical observations. Sustainable development practices will be essential for ensuring that lunar settlement enhances rather than degrades the scientific and practical value of our lunar companion. The legal and regulatory framework for lunar settlement remains largely undeveloped, with existing space law providing only general principles for activities beyond Earth. Future lunar communities will need detailed legal systems covering property rights, resource ownership, environmental protection, and dispute resolution. These legal frameworks will likely evolve as lunar settlement progresses, potentially serving as models for governance of future settlements throughout the solar system. Looking further into the future, lunar settlements could serve as stepping stones for human expansion throughout the solar system. The experience gained in establishing and maintaining lunar communities will provide crucial knowledge for missions to Mars, asteroid mining operations, and eventually settlements around other stars. The Moon may thus represent humanity's first step toward becoming a truly spacefaring civilization. The vision of thriving human communities on the Moon, with families raising children in low gravity while contributing to scientific knowledge and economic development, represents one of the most ambitious goals in human history. These future lunar residents will live in a world where Earth hangs as a blue marble in the black sky, where the physics of daily life operate under different rules, and where every breath of air and drop of water represents a triumph of human technology and determination. As we contemplate these future lunar settlements, we can appreciate both their practical importance and their symbolic significance for humanity's future. The Moon has been humanity's constant companion throughout our evolutionary history, inspiring myths, guiding navigation, and marking the passage of time. Soon, it may become our first home beyond Earth, a new world where human civilization can take root among the stars and begin the long journey toward understanding and inhabiting the cosmos that surrounds us. The gentle contemplation of these future possibilities reminds us that we stand at a unique moment in human history, when the dream of becoming a spacefaring species transitions from science fiction to engineering reality. The lunar bases of the future will represent not just technological achievements, but expressions of human curiosity, adaptability, and determination to explore and understand the universe that has given rise to consciousness and intelligence on our small blue world. As we continue our peaceful contemplation of our lunar companion, let us now explore the profound and intimate relationship between Earth and Moon. Across the vast sweep of geological time, where tidal forces and gravitational interactions have shaped not only our planet's physical evolution, but possibly the very development of life itself, there is something deeply moving about recognizing that our Moon is not merely a distant celestial object, but an integral partner in Earth's story of gravitational anchor that has influenced everything from the length of our days to the rhythm of ocean tides to perhaps the emergence of complex life from primordial seas. This Earth-Moon partnership represents one of the most intimate and enduring relationships in our solar system, a cosmic dance that has been unfolding for more than 4 billion years. The gravitational connection between Earth and Moon creates tidal forces that extend far beyond the familiar twice-daily rise and fall of ocean levels. These tidal interactions affect Earth's rotation, the Moon's orbit, and the long-term evolution of both worlds in ways that continue to shape our planetary system today. Understanding this relationship requires contemplating processes that operate on timescales ranging from hours to billions of years, connecting the familiar rhythm of daily tides to the grand sweep of cosmic evolution. When the Moon first formed through the giant impact some 4.5 billion years ago, it orbited much closer to Earth than it does today, perhaps only 15,000 to 20,000 kilometers away compared to the current distance of about 384,000 kilometers. At this close range, the Moon's gravitational influence on Earth was tremendously more powerful than today, creating tidal forces hundreds of times stronger than we currently experience. These ancient supertides would have been truly spectacular phenomena, with ocean levels rising and falling by hundreds of meters twice each day. The early Earth's rotation was also much faster, with days lasting only 5 to 6 hours. So these massive tidal cycles would have repeated every few hours in a relentless rhythm of rising and falling waters. The tidal currents generated by these extreme water movements would have been unlike anything in Earth's subsequent history. The energy dissipated by these powerful tides had profound consequences for both Earth and Moon. Tidal friction, the drag created as tidal bulges moved across Earth's surface, gradually slowed our planet's rotation, while simultaneously causing the Moon to spiral slowly outward. This process continues today, though much more gradually, with Earth's rotation slowing by about 2 milliseconds per century and the Moon receding from Earth by about 3.8 centimeters per year. The geological evidence for ancient tidal cycles is preserved in rocks called tidal rhythmites, sedimentary formations that record the daily and monthly patterns of ancient tides. These remarkable geological archives allow scientists to reconstruct the Earth-Moon relationship across deep time, revealing how tidal patterns have changed as the Moon has gradually moved away from Earth and Earth's rotation has slowed. Analysis of these ancient tidal records reveals fascinating details about Earth's distant past. Approximately 620 million years ago, Earth's day was only about 22 hours long, and the Moon was noticeably closer, creating stronger tides than we experience today. Going back further, to about 1.4 billion years ago, days were only 18 hours long, and the tidal cycles were correspondingly more frequent and intense. The influence of lunar tides on the evolution of life remains one of the most intriguing and debated aspects of Earth-Moon interactions. The intertidal zone, the region between high and low tide, represents a unique environment where marine organisms experience regular exposure to both aquatic and terrestrial conditions. Some scientists have proposed that this dynamic environment may have been crucial for the evolution of life from water to land. In the ancient world of extreme tides created by the nearby Moon, the intertidal zones would have been vast and constantly changing landscapes, where early organisms experienced dramatic shifts in environmental conditions. These challenging but predictable changes in salinity, temperature, oxygen levels, and pressure could have driven evolutionary adaptations that eventually enabled life to colonize terrestrial environments. The tidal mixing of ancient oceans may have been equally important for early life. The powerful tidal currents generated by the close Moon would have stirred ocean waters more vigorously than today, mixing nutrients, oxygen, and essential chemicals throughout the marine environment. This enhanced mixing could have accelerated chemical evolution and the development of complex organic molecules that formed the building blocks of life. Modern research has revealed that many marine organisms still follow tidal rhythms in their behavior, reproduction, and physiology, suggesting deep evolutionary connections to lunar cycles. From coral spawning synchronized to lunar phases to the navigation systems of sea turtles that may use magnetic fields influenced by tidal cycles. Life on Earth shows numerous adaptations to the Moon's gravitational influence. The Moon's role in stabilizing Earth's axial tilt represents another crucial contribution to our planet's habitability and the evolution of complex life. Earth's rotational axis currently tilts about 23.5 degrees from perpendicular to its orbital plane, creating our familiar seasonal cycles. Without the Moon's gravitational influence, this tilt would vary chaotically over geological time, potentially swinging from nearly 0 degrees to more than 60 degrees. Such dramatic changes in axial tilt would create extreme climate variations that could make it difficult for complex life to evolve and persist. Periods of low tilt would eliminate seasonal variations and create stagnant climate patterns, while periods of high tilt would create extreme seasonal contrasts, with polar regions experiencing months of continuous sunlight followed by months of darkness. The Moon's stabilizing influence has kept Earth's tilt within a relatively narrow range, maintaining the moderate seasonal cycles that characterize our current climate. Computer simulations of Earth without its large moon suggest that our planet's climate would be far less stable and predictable. The chaotic variations in axial tilt would create correspondingly chaotic changes in global temperature patterns, ocean circulation, and ice age cycles. While life might still exist in such a world, it would likely remain simple and microbial, lacking the stable environmental conditions needed for the evolution of complex multicellular organisms. The Moon's influence on Earth extends beyond tides and axial stability to affect the planet's magnetic field and interior dynamics. The gravitational interaction between Earth and Moon creates subtle but measurable deformations in our planet's shape, generating internal friction and heat that may contribute to maintaining geological activity. Some researchers have suggested that lunar tidal forces help drive plate tectonics and volcanic activity, though this remains an area of active research and debate. The synchronization between lunar cycles and various biological rhythms represents one of the most mysterious aspects of Earth-Moon interactions. Many organisms, from marine invertebrates to mammals, exhibit circulunar rhythms, behavioral or physiological cycles that match the 29.5-day lunar month. These rhythms persist even when organisms are isolated from external cues about lunar phases, suggesting internal biological clocks tuned to lunar cycles. The evolutionary origin of these circulunar rhythms remains unclear, but they may represent ancient adaptations to tidal cycles or lunar illumination patterns. In the early Earth's faster rotating world with stronger tides, the correlation between lunar phases and tidal extremes would have been more pronounced, potentially driving the evolution of biological systems synchronized to lunar cycles. Human cultures throughout history have recognized and celebrated the Moon's influence on earthly processes, from agricultural planning based on lunar phases to calendar systems that track lunar months. While many traditional beliefs about lunar influences lack scientific support, others may reflect genuine but subtle biological responses to lunar cycles that science is only beginning to understand. Recent research has revealed unexpected connections between lunar cycles and various terrestrial phenomena. Some studies suggest correlations between lunar phases and earthquake frequency, though the mechanisms and significance of these correlations remain debated. Other research has found potential links between lunar cycles and atmospheric tides, subtle pressure variations that could influence weather patterns in ways that are difficult to detect and quantify. The Moon's role in Earth's long-term climate evolution extends beyond axial stabilization to include effects on ocean circulation and heat distribution. The tidal mixing of ocean waters helps maintain global thermohaline circulation, the system of deep ocean currents that redistributes heat around the planet. Changes in tidal strength over geological time may have influenced ice age cycles and other long-term climate variations. Looking toward the future, the ongoing evolution of the Earth-Moon system will continue to affect our planet's environment and habitability. As the Moon continues to recede and Earth's rotation continues to slow, tidal forces will gradually weaken, potentially affecting ocean circulation, climate stability, and biological rhythms. However, these changes occur on timescales of billions of years, far longer than the expected lifetime of complex life on Earth. the study of Earth-Moon interactions also provides insights into the habitability of other worlds. Exoplanets with large moons may be more likely to maintain stable climates and develop complex life, while worlds without significant moons may experience chaotic climate variations that limit biological evolution. This understanding helps guide the search for potentially habitable worlds around other stars. The moon's influence on human civilization extends far beyond its effects on natural processes to include cultural, technological, and inspirational impacts. The regular cycles of lunar phases provided early humans with calendars for planning agricultural and social activities, while the moon's predictable motions helped develop mathematical and astronomical knowledge. The dream of reaching the moon drove technological innovations that continue to benefit human society. Modern technology increasingly depends on precise understanding of Earth-Moon interactions, from GPS systems that must account for tidal effects on satellite orbits, to coastal engineering projects that require detailed tidal predictions. As human activities expand into space, the moon's gravitational influence affects spacecraft trajectories and mission planning, making Earth-Moon dynamics crucial for space exploration. The Moon's role as a natural laboratory for studying planetary processes has provided insights that extend far beyond our own world. Lunar samples returned by Apollo missions contain records of early solar system bombardment that helped establish the timeline of planetary formation. The Moon's lack of geological activity has preserved evidence of processes that shaped all terrestrial planets but have been erased from Earth's surface by erosion and tectonic activity. Understanding tidal interactions between planets and moons throughout the solar system has revealed that Earth-Moon dynamics represent just one example of gravitational relationships that shape planetary evolution everywhere. From Io's volcanic activity driven by Jupiter's tidal forces to the potential subsurface oceans on Europa and Enceladus maintained by tidal heating, gravitational interactions between worlds are fundamental drivers of planetary evolution and habitability. The intimate relationship between Earth and Moon also serves as a reminder of the interconnectedness of cosmic processes. The same gravitational forces that created our Moon through catastrophic collision continue to shape both worlds through tidal interactions. The energy that powers our ocean tides comes ultimately from Earth's rotation, which was accelerated by the moon-forming impact and continues to be modified by lunar gravity. As we contemplate the moon's profound influence on Earth's history and evolution, we can appreciate both the delicate balance that makes our world habitable and the cosmic processes that maintain that balance. The gentle tug of lunar gravity that raises our ocean tides twice each day connects us to forces that have shaped our planet for billions of years and will continue to influence Earth's future for billions more. The moon hanging in our night sky serves as a constant reminder of the gravitational partnership that has made Earth a world where complex life could evolve and flourish. From the rhythm of tides that may have guided life's transition from sea to land, to the stabilized axial tilt that maintains our moderate climate, to the biological clocks that still synchronize with lunar cycles, our moon's influence permeates every aspect of terrestrial existence. In the peaceful contemplation of these ancient and ongoing relationships, we find ourselves part of a cosmic system far more integrated and interdependent than we might initially imagine. The Earth-Moon partnership represents one of nature's most elegant and enduring collaborations, a gravitational embrace that has lasted for billions of years and continues to shape the evolution of both worlds as they dance together through space and time. As we approach the gentle conclusion of our journey through lunar science, let us now weave together all the threads of discovery and understanding we have explored, creating a tapestry that reveals the profound interconnectedness of our moon's many mysteries and the remarkable story they tell about our cosmic companion. There is something deeply satisfying about reaching this point, where all the individual elements of our lunar exploration, the ancient ice hidden in eternal darkness, the magnetic anomalies and geological mysteries, the violent birth through cosmic collision, the pristine radio environment of the far side, the ambitious plans for human settlement, and the intimate relationship with Earth across geological time, begin to form a coherent, beautiful whole that speaks to the Moon's central role in our cosmic neighborhood. Our exploration began with the discovery of water ice in the permanently shadowed regions near the lunar poles, those cosmic cold traps where temperatures have remained below -230°C for billions of years. This ancient ice represents both a scientific treasure trove that preserves records of the early solar system and a practical resource that could enable humanity's expansion beyond Earth. The same extreme conditions that preserve this ice, the minimal axial tilt and lack of atmosphere that create eternal darkness in polar craters, also contribute to many of the Moon's other unique characteristics. The permanently shadowed regions connect directly to the Moon's geological mysteries and the asymmetric differences between its near and far hemispheres. The far side's heavily cratered highlands and thicker crust create deeper impact basins, where ice can accumulate, while the near side's thinner crust and large maria reflect the complex geological processes that shaped our satellite differently on each hemisphere. These differences stem ultimately from the Moon's formation through the giant impact and the subsequent evolution of the Earth-Moon system. The magnetic anomalies scattered across the lunar surface tell the story of the Moon's early history when it possessed a global magnetic field. Powered by a molten core, the gradual cooling and solidification of this core over hundreds of millions of years eliminated the global field but left behind localized magnetic signatures that continue to puzzle scientists today. These remnant magnetic fields interact with the solar wind to create the bright swirls visible on the lunar surface, demonstrating how ancient geological processes continue to influence current phenomena. The Moon's violent formation through the giant impact explains many of these diverse characteristics. Through a single, catastrophic event that reshaped both Earth and the Moon-forming debris, the collision that created Theia and Earth vaporized enormous amounts of rock, preferentially ejecting lighter materials that formed the Moon, while leaving heavier elements to merge with Earth's core. This explains the Moon's low density, its depletion in metallic elements, and its initial molten state that allowed the formation of the global magma ocean, whose crystallization created the lunar highland crust. The far side's radio-quiet environment, shielded from Earth's electromagnetic emissions by the Moon's bulk, represents one of the most valuable natural resources in the inner solar system. For astronomical research, this pristine electromagnetic environment exists because of the Moon's tidal locking to Earth, itself a result of gravitational interactions that have been slowing the Moon's rotation for billions of years. The same tidal forces that created this radio sanctuary also drive the Moon's gradual recession from Earth and the slowing of our planet's rotation. Future lunar bases and exploration missions will take advantage of all these interconnected characteristics. The water ice deposits provide essential resources for human settlement, while the radio-quiet facade offers unparalleled opportunities for astronomical research. The Moon's low gravity and lack of atmosphere simplify spacecraft operations and construction projects, while the geological stability provides secure foundations for permanent structures. The 14-day lunar day-night cycle, though challenging for power systems, offers extended periods of continuous sunlight for solar energy generation. The Moon's role in Earth's history connects all these characteristics to the broader story of planetary evolution and the development of life. The same gravitational forces that preserve the far side's radio quietude also stabilize Earth's axial tilt and drive the tidal cycles that may have been crucial for life's evolution from sea to land. The giant impact that created the Moon also established the high angular momentum of the Earth-Moon system and the rapid early rotation that created extreme tidal forces in Earth's youth. The tidal relationship between Earth and Moon demonstrates how gravitational interactions shape both worlds over geological time. The energy dissipated through tidal friction has gradually slowed Earth's rotation from the initial 5-hour day after the Moon's formation to our current 24-hour day, while simultaneously causing the Moon to spiral outward from its initial close orbit to its current distance. This process continues today, connecting the daily experience of ocean tides to cosmic processes operating over billions of years. The preservation of ancient bombardment records on the lunar surface provides crucial evidence for understanding the early history of the entire inner solar system. The Moon's lack of geological activity and thin atmosphere have preserved impact craters and other features that were erased from Earth's surface by erosion, volcanism, and plate tectonics. These lunar records help scientists understand the timing and intensity of the late heavy bombardment that shaped all terrestrial planets about 3.8 billion years ago. The isotopic signatures preserved in lunar samples tell multiple stories simultaneously. They confirmed the giant impact origin through Earth-Moon chemical similarities while also preserving records of solar wind bombardment, cosmic ray exposure, and the composition of ancient impactors. The same samples that reveal the Moon's formation process also provide insights into the early solar system environment and the processes that delivered water and other volatile materials to the inner planets. Future missions to the Moon will build upon all these scientific foundations, while also testing technologies needed for human expansion throughout the solar system. The experience gained in extracting and processing lunar water ice will inform similar operations on Mars and other worlds. The construction techniques developed for lunar habitats in the challenging environment of temperature extremes and radiation exposure will benefit settlements throughout the solar system. The international cooperation emerging in lunar exploration reflects the global significance of the scientific and practical opportunities our Moon provides. The Artemis Accords and similar agreements recognize that lunar resources and research opportunities benefit all humanity, while establishing frameworks for peaceful cooperation and responsible development. This collaborative approach builds upon the scientific traditions established during the Apollo era, when lunar samples were shared with researchers worldwide. The technological innovations driven by lunar exploration continue to benefit life on Earth through spin-off applications in medicine, communications, materials science, and environmental monitoring. The same technologies needed to sustain human life in the harsh lunar environment advance our capabilities for addressing challenges on Earth, from developing more efficient life support systems to creating materials that can withstand extreme conditions. The Moon's influence on human culture and imagination provides another unifying thread, connecting all aspects of lunar science. The same Moon that drives our ocean tides and stabilizes Earth's climate has inspired human art, literature, and mythology for millennia. The Apollo missions transformed this ancient object of wonder into a tangible destination that humans could visit and explore, while future missions promise to make it humanity's first permanent home beyond Earth. The study of lunar processes also informs our understanding of planetary evolution. Throughout the cosmos, the same impact processes that shape the Moon's surface operate on worlds throughout the solar system and around other stars. The tidal interactions between Earth and Moon provide insights into how gravitational forces shape planetary systems everywhere, while the Moon's geological evolution illustrates the processes that determine planetary habitability and evolution. The Moon's role as a natural laboratory extends across multiple scientific disciplines, from astronomy and geology to biology and physics. The lunar environment provides unique conditions for testing theories about planetary formation, impact processes, magnetic field generation, and the behavior of matter under extreme conditions. This multidisciplinary approach to lunar science demonstrates how studying individual worlds can illuminate fundamental processes operating throughout the universe. Looking toward the future, our growing understanding of lunar science will inform an expanding range of human activities in space. The Moon serves as humanity's training ground for learning to live and work on other worlds, while also providing a stepping stone for missions to Mars and beyond. The resources, technologies, and experience developed through lunar exploration will enable human expansion throughout the solar system. The environmental considerations raised by lunar development reflect our growing understanding of the Moon as both a scientific resource and a world with its own intrinsic value. Protecting scientifically important sites while enabling human utilization of lunar resources requires careful planning and international cooperation. The frameworks being developed for lunar environmental protection may serve as models for responsible development throughout the solar system. The educational value of lunar science extends from elementary school students learning about phases and tides to graduate researchers pushing the frontiers of planetary science. The Moon's accessibility to observation and study makes it an ideal laboratory for understanding cosmic processes, while its role in human history and future provides connections between science and broader human concerns. As we contemplate this integrated picture of lunar science and exploration, we can appreciate both the remarkable scientific achievements that have transformed our understanding of our cosmic companion and the exciting possibilities that lie ahead. The Moon that once seemed like a distant, unchanging object has revealed itself to be a dynamic world with a complex history, valuable resources, and crucial importance for understanding planetary evolution throughout the cosmos. The patient accumulation of lunar knowledge through telescopic observations, robotic missions, human exploration, and laboratory analysis demonstrates the power of sustained scientific investigation to unlock the secrets of other worlds. Each discovery builds upon previous knowledge while opening new questions and possibilities, creating an ever-expanding understanding of our place in the cosmic environment. The future chapters of lunar science will be written by international crews of astronaut scientists living and working on the Moon's surface, by autonomous robots exploring regions too dangerous for human access, and by advanced telescopes operating in the radio-quiet environment of the far side. These future investigations will undoubtedly reveal new aspects of lunar science that we cannot currently imagine, while also providing practical benefits for human civilization both on Earth and throughout the solar system. In the gentle integration of all these aspects of lunar science, we find a story that spans from the violent birth of our satellite through its ongoing evolution and future role as humanity's first extraterrestrial home. The Moon that has watched over Earth for billions of years is preparing to welcome its first permanent human residents, beginning a new chapter in the ancient relationship between our world and its faithful companion among the stars. And so, as our peaceful journey through the realm of lunar science draws to its gentle close, let us rest together in contemplation of what it means to share our cosmic neighborhood with this remarkable celestial companion that has been Earth's faithful partner through more than 4 billion years of cosmic evolution. Throughout our exploration together, we have discovered that our Moon is far more than the distant, unchanging orb that ancient peoples imagined. It is a world with its own complex history, mysterious anomalies, valuable resources, and profound influence on the development and evolution of life on Earth. From the ancient ice trapped in eternal polar darkness to the violent collision that gave it birth from the pristine radio silence of its hidden hemisphere, to the future human settlements that will call it home, our Moon reveals itself as an integral part of our cosmic story. The water ice deposits lying frozen in permanently shadowed craters near the lunar poles represent both windows into the solar system's distant past and keys to humanity's future in space. These ancient deposits, preserved in regions colder than Pluto where sunlight has never penetrated, contain molecular records of the comets and asteroids that delivered water throughout the inner solar system billions of years ago. Yet these same deposits may soon provide the drinking water, breathing air, and rocket fuel needed to sustain human settlements on the Moon and enable missions throughout the solar system. The mysteries and anomalies we have contemplated, from magnetic swirls that deflect the solar wind to the asymmetric differences between the Moon's hemispheres, remind us that even our most familiar cosmic neighbor still holds secrets waiting to be unraveled. The Apollo samples that revealed ancient magnetism in rocks from a world that lacks a global magnetic field continue to challenge our understanding of how planetary magnetic fields form and evolve. The unusual geological features and unexplained phenomena observed by astronauts and spacecraft demonstrate that exploration and discovery are ongoing processes that reveal new wonders with each mission and analysis. The giant impact that created our Moon through cosmic violence of almost unimaginable scale connects us to the fundamental processes of planetary formation that shaped our entire solar system. This catastrophic collision between the early Earth and the Mars-sized world we call Theia not only created our lunar companion, but also established the high angular momentum. That gives us our 24-hour day and the tidal forces that continue to shape both worlds. The moon that emerged from this cosmic destruction has profoundly influenced Earth's subsequent evolution, demonstrating how creation and destruction are intimately linked in cosmic processes. The radio-quiet environment of the moon's far side represents one of the most precious natural resources in our cosmic neighborhood, a sanctuary of electromagnetic silence, where sensitive instruments could detect the faintest whispers from the early universe without interference from Earth's growing bubble of technological noise. This pristine environment exists because of the same tidal forces that keep the moon's rotation synchronized with its orbit, ensuring that one hemisphere always faces away from Earth, and its electromagnetic emissions. The future lunar bases and exploration missions we have envisioned will transform our relationship with our celestial companion from distant observation to permanent residence. The Artemis program and other international efforts promise to establish humanity's first extraterrestrial settlements within this decade, creating communities that will live and work in an environment of low gravity, extreme temperatures, and constant radiation. These future lunar residents will utilize the moon's resources while conducting scientific research impossible on Earth, serving as pioneers for humanity's eventual expansion throughout the solar system. The intimate gravitational relationship between Earth and Moon has shaped both worlds across geological time through tidal forces that continue to operate today. The same lunar gravity that raises our ocean tides twice daily has gradually slowed Earth's rotation, moved the Moon away from our planet, and may have created the intertidal environments where life first made the transition from sea to land. This cosmic partnership has stabilized Earth's climate, moderated its axial tilt, and provided the predictable cycles that may have been crucial for the evolution of complex life. These diverse aspects of lunar science come together to tell a coherent story of cosmic evolution, planetary formation, and the development of habitable worlds. The Moon serves as both a record of our solar system's violent early history and a laboratory for understanding the processes that shape planetary environments throughout the universe. Its influence on Earth demonstrates how gravitational interactions between worlds can create the stable conditions necessary for the development and persistence of complex life. The international cooperation emerging in modern lunar exploration reflects the global significance of our Moon's scientific and practical value. Unlike the competitive space race that drove the Apollo missions, current lunar exploration emphasizes collaboration, resource sharing, and peaceful development for the benefit of all humanity. The Artemis Accords and similar international agreements establish frameworks for responsible lunar development that protect both scientific sites and the interests of all nations. The technological innovations driven by lunar exploration continue to benefit life on Earth, through applications ranging from medical devices to environmental monitoring systems. The extreme conditions of the lunar environment push the boundaries of engineering and materials science, leading to advances that find applications in terrestrial industries. The closed-loop life support systems needed for lunar habitats contribute to sustainability technologies on Earth, while the precision navigation required for lunar missions improves GPS and other location-based services. Our Moon's role as Earth's companion extends beyond gravitational interactions to include cultural, inspirational, and educational influences that have shaped human civilization throughout history. The regular phases of the Moon provided early calendars for agricultural societies, while its predictable motions helped develop mathematical and astronomical knowledge. The achievement of landing humans on the Moon demonstrated humanity's capability to transcend planetary boundaries and explore the cosmic environment. The study of lunar science also connects us to fundamental questions about planetary habitability and the potential for life elsewhere in the universe. The Moon's influence on Earth's stability and habitability provides insights into what makes worlds suitable for complex life. The search for similar Earth-Moon partnerships around other stars could help identify potentially habitable exoplanets where life might develop. and flourish under stable conditions. Looking toward the future, our moon will continue to serve multiple roles as humanity expands into space. It will be our training ground for learning to live and work on other worlds, our refueling station for missions throughout the solar system, and our laboratory for conducting research impossible in Earth's environment. The technologies and techniques developed for lunar operations will enable human settlement of Mars and other destinations, making the moon a crucial stepping stone for becoming a truly spacefaring species. The environmental protection of the moon represents a new challenge as human activities expand beyond Earth. Balancing scientific preservation with resource utilization requires careful planning and international cooperation to ensure that the moon's unique environments and historical sites are protected while still enabling human use of lunar resources. The frameworks being developed for lunar environmental protection may serve as models for responsible development throughout the solar system. The moon's future as a world of human settlement will create new relationships between Earth and its companion. Lunar residents may develop distinct cultures adapted to the unique environment of low gravity, long days and nights, and isolation from Earth. These future lunar societies will be connected to Earth by communication links and supply chains, but will also develop their own traditions, governance systems, and ways of life shaped by their extraordinary environment. The scientific discoveries that await future lunar exploration promise to revolutionize our understanding of planetary evolution, solar system history, and the processes that create habitable worlds. Samples from the moon's facade, deep drilling into ancient impact basins, and long-term observations from lunar observatories will reveal new aspects of our cosmic neighborhood that we cannot currently imagine. Each new discovery will likely raise new questions while deepening our appreciation for the complexity and beauty of cosmic processes. The economic development of lunar resources may eventually transform space exploration from a primarily scientific and exploratory endeavor into a sustainable economic activity. The extraction of water, rare metals, and other materials from the moon could create new industries and economic opportunities, while reducing the environmental impact of resource extraction on Earth. The moon's low gravity and lack of atmosphere may make it an ideal location for manufacturing processes that benefit from these unique conditions. As we contemplate our eternal companion's secrets and our evolving relationship with this remarkable world, we can appreciate both how far our understanding has progressed and how much remains to be discovered. The moon that seemed like a simple, unchanging disk in ancient skies has revealed itself to be a complex world with a dynamic history, valuable resources, and continuing influence on Earth's evolution. Yet each new discovery about our lunar companion raises new questions and opens new possibilities for exploration and understanding. The gentle rhythm of lunar phases that has marked the passage of time throughout human history will continue as humanity establishes permanent settlements on the moon's surface. Future generations may grow up seeing Earth as a blue marble hanging in the lunar sky, developing perspectives on our cosmic environment that we can barely imagine. These future lunar residents will carry forward the human tradition of exploration and discovery, while creating new chapters in the ancient relationship between Earth and Moon. In our peaceful contemplation of these lunar mysteries and future possibilities, we find ourselves part of a story much larger than our individual lives, a cosmic narrative that connects the violent formation of worlds to the gentle development of life. From the ancient bombardment that shaped planetary surfaces to the future expansion of consciousness throughout the solar system, our moon serves as both a record of this cosmic history and a gateway to humanity's future. Among the stars, the secrets our eternal companion still holds promise to inspire and challenge future generations of explorers, scientists, and settlers who will call the moon home. As we conclude our journey through lunar science tonight, we can rest in the knowledge that this is just the beginning of humanity's relationship with our celestial companion. The moon that has watched over Earth for billions of years is preparing to welcome its first permanent human residents, beginning a new epoch in the ancient partnership between our world and its faithful satellite. Good night from the sleepy scientist.